Carlos is a theoretician, and he will talk for us this afternoon, but I would like to call the moderator of this afternoon, that is Felipe Silva. Felipe Silva is my oldest student, and now he is professor of the University of the State of Amazonas. And he is working on CMS on RPCs. Okay, go ahead, Felipe.
Hey, thanks, Professor Santoro. Good morning, good afternoon, good evening for everyone. We start our afternoon session. We have a quite packed agenda, so I kindly ask the speakers to stay in time. And also just to remind the attendees, if they have a question, they can use the Q&A button on the bottom of the Zoom window. We start this session with, as Professor Santoro already said, with a talk with Professor Carlos Canal. Professor Carlos Canal is an emeritus professor of the Department of Physics of Universidad Nacional de La Plata, where he also took his PhD. He worked with particle physics and quantum field theory. He also was a fellow of the Guggenheim Foundation and visiting researcher of many institutes such as European universities, ICTP, CERN, and CBPF. Professor Carlos, the floor is yours. I believe you have 30 minutes.
Thank you very much for the introduction. I will share my screen. And I think it's going on here. Okay. First, what is first? Thanks a lot to Alberto Santoro for the kind invitation to participate in LISHEP 2021, and also to all the organizers, and in particular to Eduardo Reboredo. I do not resist the temptation of telling you that in Brasilia in 1965, 56 years ago, please do not calculate our age, I was teaching electromagnetism, and Alberto Santoro was one of the students in the course. I think that he liked the lectures because he has invited me to talk at LISHEP several times. I strongly hope that after my presentation of today, you can feel similarly to Alberto. Okay, the most clear title of my talk should be Neutrinos and Strong Dynamics, QCD and Beyond with a question mark. The first question to pose and to answer seems to be, what has to do a neutrino that only participates of the weak interactions with QCD, the theory of strong interactions? Through this talk, we hope that it will become clear that no doubt the neutrino has a lot to do with QCD. I'll begin with a history, or a small history, a brief history, perhaps story, because I'll be involved in it. It starts in the 70s when the quark structure of nucleon, the proton in particular, was confirmed by the experimental data obtained in the Gargamel barbell chamber at CERN, acted by neutrino beams, and it continues nowadays, mainly in connection with the ice cube detected events initiated by very energetic cosmic neutrino in this case. Well, the experimental study of electroinelastic scattering at SLAC and the results obtained at CERN in the bubble chamber Gargamel in the 70s, detecting neutrino reactions, gave strong support to the image of the nucleon containing particular constituents, called partons initially, but afterwards were identified with the quarks of the SU3 flavor spectroscopy hypothesis. Initially, Data confirm the scaling behavior of deep inelastic cross-sections, and moreover, that the electric charge assigned to quarks was confirmed. Gargamel apparatus owes its name to the mother of Gargantua, the character of Rabelais in his series of books called Gargantua and Pantagruel, mainly due to the big size of this bubble chamber. It measures something like 5 meters long and 2 meters diameter, and weighted something as 1,000 tons. In July 73, the Gargamel collaboration announced the detection of weak neutral currents, being the first experimental indication of the existence of the Z0 weak boson, and for that reason, a verification of the electroweak theory based upon the SU2 cross U1 gauge symmetry was confirmed. Unfortunately, in 1979, an irreparable crack appeared in the bubble chamber and Gargamel was decommissioned. It is at present part of the microcosm exhibition at CERN. At that time, I remember, the cracking was particularly impressive because the tank of Gargamel was built by the same industry that constructed nuclear reactor tanks at that time. Imagine. This cracking is directly connected with my participation in the physics of Gargamel. Together with the Brazilian colleagues, Maria Beatriz Gay and José Martins Simões, we were contacted in Strasbourg by one of the experimental collaborations working in Gargamel. The Aachen, Bergen, Brussels, London, Strasbourg collaboration that wanted we to compute the expected number of same-sign dimuon events in neutrino nucleon scattering to be expected, taking into account the small time of recording of data due to the decommission of the bubble chamber. By using the QCD improved Parton model, we concluded that the collaboration could have registered at most 5 dimuon events. We said at that time, if they were democratic, each member of the collaboration should get 1 event. In 1961, I remember you that Gelman, based on the symmetry group SU3 flavor, introduced the eightfold wave scheme, which classified the hadron into a representation of that group. Mathematically, Gelman's SU3 model has a fundamental representation of dimension 3, that perhaps would imply the existence of 3 more elementary particles that were called by Gelman quarks. At the same time, Zweig, in a paper of 1964, proposed that mesons and baryons are formed for a set of 3 fundamental particles that he called aces. Both Gelman's quarks and Zweig's aces had exotic electric charge equal to +2/3 and -1/3 of the electron charge. The situation at that time, 1966, was such that Gelman himself stated, "The idea that mesons and baryons are made primarily of quarks is hard to believe." As it was previously mentioned, in 68, electron-proton scattering experiment at MIT, SLAC collaboration at SLAC, revealed the inner structure of proton. The experiment was based on electron colliding protons and the detection of the electrons that emerge. In the subsequent years, these results were confirmed and combined with those from neutrino scatter in the Gargamel bubble chamber at CERN, showing conclusively that these point constituents have charges of -1/3 electron and +2/3 electron. Just to remember briefly this conclusion, remember that the scattering on proton you describe in terms of unknowns that are called structure functions that are related through the electric charge of the components of the nucleon with the quark distribution functions of each class of quarks involved. For a proton target, F2 gamma proton reads like that, with a 4/9, a 1/9, and a 1/9, some exotic numbers due to the electric charge of the quarks. And for the photon neutron scattering, you define a corresponding structure function exchanging U with D. For neutrinos, the more elementary interactions are muon D, lepton U, and mu U bar, lepton D bar, and the F2 neutrino proton and neutrino neutron are written there. So if you consider an isoscalar target nucleon, the relation between F2 neutrinos and F2 photons reads like this in red there, and is larger or equal than 5/18. Well, the comparison between the data from SLAC and the data from the Gargamel bubble chamber is here presented, the original data as it appears in the original paper, and it shows that there are exactly a correspondence between the deep inelastic scattering initiated by a neutrino and by the charged leptons. And this 5/18 is already present in the data. So neutrinos give physical sense to the fractional charge of quarks. Remember that quarks are the so-called degrees of freedom of the QCD theory of strong interactions. Oh, it is clear that much water has gone under the bridge Gargamel, since the Gargamel success, and we are not trying here to summarize the recent history of the neutrino physics. We are only interested in presenting one of the most recent approach of using the very high energy neutrino data to eventually confirm at these energies QCD or detect new physics beyond the standard model. It is important to realize that even if neutrino participates directly only on the wave interaction, leaving aside gravity, of course, they are very useful as proofs of the structure of hadrons, and in particular of proton structure, as it was remarked before. So the fact is that high energy neutrinos are unique messengers of information of very far away physics phenomena. For this reason, they could be eventually considered as an informant of physics that happens there beyond the standard model. The event rates that one could register are a combination of neutrino flux coming from very far distances and the corresponding cross-sections. In order to avoid the astrophysical uncertainties that are always clouding particle physics implication, one can use the concomitant consideration of upgoing and downgoing neutrinos, one's coming from the sky, the other coming through the Earth. And this is precisely the job that IceCube collaboration, the IceCube Observatory, the neutrino telescope installed in the Amundsen-Scott station of the South Pole, is doing for us. This is precisely a counting experiment that is what we will use in the following. So we have investigated together with Luis Anchordoki and Jorge Soriano from New York, the sensitivity of the present and future South Pole neutrino detection experiment. in particular on the neutrino-nucleon cross-section. This was triggered by the announcement of the IceCube collaboration that they have registered non-zero neutrino event rate of energy for PeV. This is the announcement in this archive and afterwards published paper. The IceCube Neutrino Observatory at the South Poles detects spherical light from charged particles produced in neutrino interactions and firmly established the existence of an astrophysical high energy component. They particularly refer to the so-called HESE events, high energy starting events, those that start inside the detector, and in this way the muon background is substantially reduced. And for energies above 60 TeV, the measured flux is this written here. So it is necessary to go up to the Antarctic and to meet the IceCube experiment. This is a very nice map of South America that did our Uruguayan painter Torres Garcia. Nothing to do with my family. So we went to the Antarctic, and there is installed IceCube, some 86 strings of domes set 125 meters apart, one to the other, that are inside the ice in the Antarctic up to down to 2,500 meters mostly, and they detect there the arrival of neutrinos. Those are examples of the detection. And this is a surface view of the full IceCube detector for one event in red, and those here at the right are the Bert and Ernie events, as they call these very nice events registered. Well, the IceCube is able to determine the cross-section neutrino nucleon, and this is the number they presented, is consistent within errors exactly with the standard model prediction. And the interesting thing is that also IceCube have proposed an upgrade that is called IceCube Gen 2, an order of magnitude larger in aperture, and this will allow a precise measurement of sigma neutrino nucleon comparable to the one obtained via perturbative QCD from collider data. Well, with these colleagues, we have a main goal in front, that is to infer the sensitivity of IceCube to sigma neutrino nucleon. We remark that the energies in here for the neutrinos are well beyond those available from neutrino beams. And so we can count event rates, or they can count event rates, well done, combining upwards and downward going neutrinos. So this analysis was first done fixing the relation between the charged current weak interaction and the neutral current weak interaction, as is in the standard model, that is 3, almost 3. And in a second analysis, we'll leave this relation as a free parameter, because we are sure that eventual non-perturbative standard model phenomena are will appear in modifying the sigma neutral current. Here, for here only for to do a more precise detail of the talk. I have included all the details of the neutrino interaction, both for charged currents and for neutral current, for all taking into account that there are 3 flavors of neutrino. I will skip this for because it's present in my transparency. There are that you can consult every time. Those are the kinematical variables. This is the reference cross-section in terms of the known physics up to now. This is written for W, and similar expressions are with W replaced by Z for the neutral current case. Well, at the leading order in QCD, these structure functions are written in terms of the quark distribution functions like this, as it is presented here in this transparency. I will skip it. It is interesting to mention that there are different signal morphologies coming from the experiment, and this is connected with the fact that the charge current interaction of electron neutrino, mu neutrino, and tau neutrino is different from the interaction that charge current of electron as tau present and neutral current present. The T is for track, the S is for shower. Of course, misclassification is possible, but when neutrino interacts with ice, you have those different topologies that are present here in this example. You have the trace for a neutrino muon, and you have a shower, a cascade for neutrino electron, and for all the neutral current case. There are also possible double band coming from neutrino tau, as you know, because the neutrino tau will produce a tau, and the tau will afterwards decay in hadrons. The shower is a spherically symmetric signal, so there is a low angular resolution, but you can do a precise measurement of the energy of the neutrino electron, for example. And the track, the neutrino muon travels through the ice. To infer arrival direction is better, but the deposit energy is only a lower bound for the electromagnetic energy, the total electromagnetic energy. So we consider down and upgoing events, and the experimental evidence is through the number of events that those coming from down are the neutrino flux times the cross-section for the different interaction and for different neutrinos, and the up-down number of events is proportional to the neutrino flux and also to the cross-section, of course, but divided by the attenuation cross-section due to the fact that the neutrino is traversing the Earth. The ice cube shows that, or determine that the direction of arrival of the neutrino is isotropical, and also that there are more or less exactly the same fluxes for the 3 flavors of neutrino: neutrino electron, neutrino muon, or neutrino tau. The reference cross-section that one considers, and also the experimental collaboration, is those determined by Cooper, Sarkar, and Sarkar, and they are shown here for isoscalar target, for charged current and neutral current, using HERA DF 1.5 determination of the structural functions. So we present then we did a likelihood analysis, a maximum likelihood estimation. The tool for the analysis was this. This likelihood states how probable a set of observations are given particular values of the statistical parameters. To go ahead, one introduces the set of parameters F and H, one related to the flux and one related to the sigma total of reference. And then you do the data analysis, trying to find the maximum of the likelihood that allows one to estimate the most likely values of those parameters F and H. The values that are obtained in this way, as I have discussed, and the set of parameters for the likelihood that we obtain are those expressed here, H and F, both compatible with 1. And this here is the 1, 3, and 5 sigma confidence contours for F and H, for scalar total cross-section and flux with respect to the reference values. The cross-section then is consistent and 1 sigma with the value from QCD guided by hero data. So that the problem is that the statistic is limited around 37% of uncertainty. So the next step was to leave sigma CC over sigma NC as a free parameter because all new physics processes in general increase the neutral current cross-section. The new physics could be gravitons, strings, Phaleron. Here is a reference where all those possibilities were analyzed. And new physics in general via new Z prime, for example, or black hole or string excitation, all will be will produce an enhance of the neutral current cross-section. It is interesting to mention that an analysis previous of those of this experimental data was done by IceCube that only uses outgoing tracks, only T events, track events, and cannot measure enhancement of sigma neutrino nucleon. And those colleagues, Bastamante and Canoli, they fixed for neutrino and antineutrino 1/3 for the relation between charge and current and neutral current, and they use only S events expected in the standard model. And on this 1/3, our proposal is complementary. All S plus T data was used, and the sigma CC over sigma NC was taken as a free parameter. That means that the sigma total that we wrote as CC0 plus CNC, leaving C sigma NC as a free parameter, as I said, and we perform a new likelihood analysis, maximizing the likelihood function, and for those F and S and C parameters, and those are the results that showing again that all is compatible with the standard model. The cross-section is consistent at sigma with the value from QCD guided by hero data. But it's interesting that in some sense, we can consider this result as a constraint from IceCube on non-perturbative standard model phenomena. Well, let's go ahead and looking ahead in terms of the IceCube Gen 2 upgrade. That is an apparatus very similar to IceCube, instrumented with a volume of 10 square kilometers, and is in some sense the future of neutrino astronomy in Antarctica. This will correspond to an order of magnitude increase in exposure per year, and for IceCube Gen 2, we adopt a multiplicative factor on the IceCube data sample, because 10 years of IceCube Gen 2 will give rise to data with something like 500 neutrino events for these energies. And if 20 years of working is possible, 1,000 neutrino events, this means a multiplicative factor of 20 or 40 in 10 or 20 years. And we perform with the sample the same likelihood analysis done for real data. The precision on the cross-section goes now with 500 events to almost 8%, and with 1,000 events, 5.5%. This is comparable to that obtained in perturbative QCD calculation from HERA data. Well, of course, there is also a dream that an IceCube-like experiment with an apparatus of 100 square kilometers. That means 500 or 1,000 times the actual sample, and the precision with this could be of the order or less than 2%. This is the evolution of the uncertainty of the cross-section that we determine, and we see that if this experiment goes ahead, we have this possibility of relative uncertainty of some percent, less than 10. Well, before that means that the IceCube is opening other doors to look for new physics, of course. So before ending, we refer to the FACET new forward search experiment new in LHC at CERN. This is an experiment designed to detect collider neutrinos directly in order to analyze the neutrino cross-section at the TeV energies of LHC, the region of energy not yet studied, not yet analyzed. And it is interesting that on May 13, some couple of months ago, the first evidence of neutrino interaction at LHC was announced, and the event display is shown here in this figure that shows a very nice events detected at FACET new. So, as a conclusion, neutrino have and will have a lot to say about the strong dynamic. We have recalled the importance of neutrino data in giving physics reality to the fractional charge of quarks, and recently, the IceCube observation informed about the strong dynamics with the neutrino telescope in the Antarctic. So, as a finale, new something to say? Yes, a lot. Thank you very much. After this, I would like to say that feel free to ask questions, to make comments, to make critics, and eventually to make compliments to this address, this email address. It will be quite difficult for me answer question here because I have some trouble with the audio, but anyway, I will try hard. Thank you very much, and thank you very much to the organizers.
Thank you, Professor Canal. Thank you a lot for the very nice and detailed talk. I don't see any raised hands, neither questions on Q&A. Mr. Trump suggests that if anyone wants to get any further details or ask any question, get in touch straight with Professor Canal. Thanks a lot.
Thank you.
With this, we can go ahead to our next Professor Carlos Arla Bernal, which I believe is connected.
Can you hear me?
Yes, I hear you.
And let me just share my slides, 1 second.
Sure. Professor Carlos Avila is a professor of physics at the University of Los Angeles. He took his PhD in Cornell University in 1997, which is then he's actively working in research on high energy physics. The past he worked for experiments E710, E811, and the Zero at FNAL on the study of diffractive processes. Nowadays, he's also a member of the CMS collaboration, where he and his students, they actively participate in the RPC subsystem and supersymmetry searches. Professor Carlos, I believe you have 30 minutes when I stop.
Okay, thank you. Can you hear me?
You very well.
Okay. So let me just start by thanking the organizers and especially Professor Alberto Santoro for the invitation to participate in this workshop. And this talk will be a description for the comparison of a proton-proton and proton-antiproton elastic differential cross-section measurements performed by TOTEM and D0 experiments. Here is my email for questions or comments. And the talk outline is as follows. First, I will just provide a short introduction about the Oderon and its impact on the elastic differential cross-section. And then I will briefly describe the measurements performed by D0 and TOTEM experiments on the sigma dt, which are at different center of mass energies. And therefore, to make a comparison, we have to do a kind of an extrapolation. I will describe details about the extrapolation and the comparison, show you the results we are getting, and make some concluding remarks. So let me start by talking about the Oderon. For that, we have to refer to Regge theory. Here is an article, recent article giving a review about Regge theory. One of the main results from Regge theory is the fact that the poles in the complex angular momentum plane follows on Regge trajectories, that these trajectories actually dictate the behavior of the scattering amplitude at high energies as a power law of the center of mass energy of the interaction. Here, the Regge trajectories are usually parameterized as a linear parametrization that just give how the poles in the complex angular momentum plane depend on the square of the quadratic momentum transfer. And here is a scale for energy, which is usually set at 1 GeV square. The optical theorem shows that the total cross-section depends on the imaginary part of the nuclear scattering amplitude in the forward direction. Therefore, when one looks at the total cross-section will depend on energy, but the exponent of the dependence comes from the intercept on the Regge trajectory. There have been already Regge trajectories observed and measured for families of meson exchanges, but the intercept of these meson trajectories is about 0.5. That means that the total cross-section from these meson trajectories will change with energy and will be reduced as energy increase as a square root of S. That would explain the behavior of the total cross-section at low energies. And then, but at some point, the experimental data shows that at high energies, the total cross-section is increasing with energy. Therefore, there should be another trajectory that is being exchanged according to Regge theory, and that would be a Pomeroy trajectory, which one can see that it corresponds to a even charge conjugation trajectory. In 1973, Lukasov and Niculescu also made us aware that there could be also possibility to have a trajectory that is exchanged, which has an intercept also near 1, but also is odd on their charge conjugation, and that would be the Oderon. So that is basically the explanation from Regge theory. And from non-perturbative QCD, one can see that the Pomeroy is being exchanged in a proton-proton elastic collision. And then what it is being exchanged could be a T-channel exchange of a colorless 2 gluon bound state at leading order. The case of the Oderon could be a T-channel exchange of a colorless 3 gluon bound state, also leading order. Certainly in the S-channel, Pomeroy and Oderons could be an indication of gluons of 2 or 3 gluons being exchanged respectively. There is a talk in this workshop about globules. So for people who wants to learn more about globules, I refer you to the talk by Professor Felipe Llanes Estrada on Thursday. The fact that it is easier to make two gluon-bound state as compared to 3 gluon-bound state, that means that the Pomeron contribution to the scattering amplitude will be much higher than the Oderon contribution. So the next question is how we can observe effects from the Oderon. And at high energies, certainly the meson trajectories will have a negligible contribution, and the contribution will come mainly from the Pomeron contribution to the scattering amplitude and from the Oderon contribution. And from quantum mechanics, we know that the sigma dt depends on the square of the modulus of the scattering amplitude. And then doing charge conjugation, we can obtain the sigma d p-bar, but there will be a change in sign here for the Oderon contribution. So at some places in the sigma dt, we should be able to observe some differences between the two elastic differential cross-section measurements, and these differences could be somehow interpreted as some effect coming from this contribution from the Oderon amplitude. So here I am showing on the right some data already published at 53 GeV, ISR data, where there is a comparison of the p-bar elastic scattering and the proton-proton elastic scattering for the sigma dt, and there is a difference observed near the diffraction minimum at about 3 sigma level. However, the center of mass energy is quite low, that some meson trajectories could still play a role, so it is hard to make a conclusion that actually this difference comes from the Oderon. Another observable for Oderon effects could be to look at the evolution of rho and the total cross-section with the square root of S, where rho is the ratio of the real to the imaginary part of the nuclear scattering amplitude in the forward direction. And this is what a recently TOTEM experiment published in 2019, and I show you in the next slide. Here on the left, you see measurements of the total cross-section performed by TOTEM experiment at 4 different energies, 2.76, 7, 8, and 13 TeV. And on the right, you see measurements performed for the rho value at 8 TeV and 13 TeV. And actually, the measurements performed at 13 TeV are quite precise with the small error bars. And you see on top of the measurements some theory models that try to interpret the data, and these theory models correspond to models that only take into account Pomeron effects, so only include Pomeron. And you can see that, for example, some models could describe very well the total cross-section measurements, but those models don't describe at all the raw measurements at the 13 TeV especially. And the same, there are some theory models being that are based on Pomeron exchange only that describe the raw measurements, but they poorly describe or not describe at all the measurements of the total cross-section. So then TOTEM in this article, they excluded these models at the level of 3.4 to 4.6 sigma level for the range of models, and is an indication that Pomeron-only models cannot explain how rho and sigma tot is evolving, and then some odd amplitude contribution, odd means under charge conjugation, could be the one to explain this data together. In this slide, let me just show you quickly the general structure of the elastic differential cross-section at the TeV energies. At very low T values, below 10 to the -3, we have a dominant contribution from the Coulomb scattering amplitude. Then between 10 to the -3 and above, we have a dominant contribution from the nuclear scattering amplitude. There is a phase difference between the two scattering amplitudes, and that's why we see a Coulomb nuclear interference at about 10 to the -3. Beyond the second diffraction minimum that is over here, here is the first diffraction minimum, sorry, here is the second diffraction maximum is what I meant. Beyond that, we enter into the perturbative QCD regime where we see that the sigma dt falls off as a power law in T. Just to make you aware what is needed to reach these very low t values. For example, if we take 10 to the minus 3 in this quadrimomentum transfer equation from the Mandelstam variable, we can approximate it, the sine square as basically the angle. And then for 1.96 step to reach t values of 10 to the minus 3, one would need to reach angles of 16 microradians, and at 13th step, one would need to reach angles of 2 microradians. Those are very small angles, and usually what happens is that the elastically scattered protons or antiprotons would remain within the vacuum tube pipe, and then one needs a mechanism to really get the detectors very close to the beam, and that's why Raman pods are used, and the detectors are located inside the Raman pods, and the Raman pods have to be located very far away from the interaction point, and use some special beta optics in the accelerator to allow to squeeze the beam sizes at the detector locations, and then measure the coordinates of the detectors, and from the coordinates get the scattering angle, and then from there get t, count the number of events as a function of t, correct for acceptances, efficiencies, and take into account the normalization given by the integrated luminosity, and get the sigma dt. So let me show you briefly the measurement performed for the elastic differential cross-section for p-pbar at this zero experiment at the energy of 1.96 step. This is a small drawing showing the setup with Raman pods at both sides of the interaction point. Here are the locations, and actually probably the best name is not Raman pods, at least for the D0 experiment, but actually Brazilian pods. These pods were made by the Brazilian colleagues led by Professor Alberto Santoro, and they were designed, constructed, installed, and operated by the Brazilian team. Within the Raman pods, or Brazilian pods, in this case, there were fiber scintillating detectors that allow us to measure the coordinates of the elastically scattered p-bars and protons. And here you see below some plots that show the correlations between the coordinates on the proton detector and antiproton detector, with some background that it comes mainly from beam halo. Since we had timing information, we could just tag the events that have a time of flight that is consistent with particles being scattered at the interaction point, or particles that somehow go with the beam bunches but do not have a correct timing from a time of flight that allow us to measure the beam halo. Here is what, after doing all the corrections, we were able to measure, and it's the sigma dt. As a function of t, we see a fall off, an exponential fall off of the sigma dt until reaching some t value where the sigma dt flattens out, but we do not observe any diffraction minimum nor a second diffraction maximum. We cover this t range over here. Now we want to compare with the measurements performed by TOTEM experiment. So let's describe briefly the measurements by TOTEM. TOTEM use basically the same principle, use Raman pods very far away from the interaction point, use different high beta optics for the different measurements. Actually, it's interesting, the different high beta optics that they reach. This one, 2.5 kilometers beta value, this high beta value allows to really get the detectors very close to the beam and get into the nuclear Coulomb interference region and measure rho, and that is why this one is over here. Here are the references for measurements performed at 3 different center of mass energies, and when you compare the sigma dt's from proton-proton collisions at these energies, you actually can see the diffraction minimum and the second diffraction maximum very well identified by the data. So let's put together all the data around the place where we see some differences, that the places around the minimum that we call the dip and the second maximum that we call a bump. So the question is, we have this red measurements at different energies from proton-proton collisions and the p-pbar data at 1.96 TeV. Now we have to define how we do the comparison, and different approaches could be followed. One simple approach would be compare the two closest energies and account with some systematic uncertainties because of the change of energy, and then see the structure of the sigma dt and try to make conclusions from there. As you see, it would be difficult to somehow make estimates of the systematic uncertainties. Other possibility would be to use some function motivated by some theoretical model and feed all, for example, all the proton-proton data and then extrapolate the function to the 1.96 TeV case and then compare with the measurement. But then that would be model-dependent study. So the approach we follow is like data-driven study that we see from the data itself how it takes some characteristic points and see how the data evolves with energy. And this is what I'm going to show you. Before showing you that, some also simple approach one could follow as a first step is to look at the sigma dt value at the bump and the sigma dt value at the dip and take the ratio and see how this ratio evolves with energy. So let me show you that. Take the ratio of the sigma dt at the bump position, the sigma dt at the dip position, and then since these black points could correspond to the measurements performed by TOTEM, and since we don't see at 1.96 TeV from p-pbar data nor dip nor bump, we just quote a value of r equals 1 and see from the data points near the dip, near the bump, according to what we extrapolate from proton-proton data, see what variations those points have, and then quote some uncertainty. And then we could also compare with lower energy data for p-pbar, and we see that actually that ratio remains very much flat around 1. And the ratio from lower data for proton-proton elastic scattering, actually the ratio goes down with energy up to a value of about 100 GeV and then flattens out. Given this observation, and assuming that it is flat all this way, one can do an extrapolation from the proton-proton data to 1.96 TeV and compare to the p-pbar data at the same energy. And then you can see that from this simple measurement, there is already more than 3 sigma difference between the extrapolation and the data. But again, some people could criticize that, for example, this extrapolation assumes it's flat in a huge energy range where actually we don't have measurements. And that's why we go to some more strict comparison, and is the following. Since the interest is about the region where we see the dip and the bump, then we take from the data itself the values of the sigma dt and the values of t for the dip, the bump, and points around that region, taking in total 8 characteristic points, and see how the t values and the sigma dt values evolve with energy. That's what I'm going to show you next. So these are the measurements performed for the 8 characteristic values at the 4 different energies. The 4 different energies cover a 10 TeV energy range. We only have to do an extrapolation from 2.76 TeV to 1.96 TeV. So it's actually a small extrapolation of about 8% compared to the overall range where there are proton-proton measurements. So all the characteristic points, when we look at the t-value and see how the t-value changes with the square root of s, we get by observation, experimental observation, trying to parameterize what we observe with a simple function to parameter function, how t evolves with energy. And this is what we find. And you can see basically the fits here, and then the fits allow us then to predict or make an estimate on the t values for the 8 characteristic points at 1.86 TeV. The same we do for the sigma dt at the square root of s, and then we also see how they evolve with energy, and this is the function that we found that describes very well how they evolve with energy. So now we have already the extrapolation from the proton-proton data at the center of mass energy of 1.96 TeV. Now we have to get ready to make the comparison, but for making the comparison, we have to take into account two things. I will explain you what things they are. First, let's take a look at the 4 measurements made by TOTEM for the 4 different energies, and the black dots here corresponds to the 8 characteristic points that were extrapolated. And if you see, they follow the pattern that we observe as a function of energy. But the t values that were used for the D0 measurement, they occur at different t values. So in order to make the comparison, we have to do a kind of interpolation between the characteristic points to somehow evaluate the comparison at the same t values. For doing that interpolation, we use a double exponential function that is motivated very much by the data, that somehow this double exponential function describes the structure of the sigma dt measurements for the 4 energies, and also describes the p extrapolation. And using that, we get the points, 8 characteristic points at the same t values of D0 data to make the comparison. We also have to determine the error band, and for doing that, what we do is take different Monte Carlo ensembles, just allowing the Gaussian uncertainties from each characteristic point to vary one at a time, and do many experiments and do the interpolation fit for any of the pseudo experiments we do, and that's how we determine the error band. So we are ready to compare. Here is basically the extrapolation of proton-proton, the sigma dt at 1.96 TeV using the TOTEM data. But to compare, we are interested on the shape of the distribution. And because of that, we fix the normalization. And how we fix the normalization? We require that both TOTEM extrapolated data and the measured the sigma dt at 1.96 TeV have both the same optical point, which means the same d sigma dt at t equals 0. So for the case of the D0 data, since we see the exponential fall off before the dip, we just do that fit of the exponential fall off and determine A. This is the value we get. For the case of the proton-proton TOTEM data, we use the optical theorem. And since we are interested to get the sigma dt estimated at 1.96 TeV and now get the optical point, then we have to also make a small extrapolation to get the sigma tot value at 1.96 TeV for proton-proton. Here are the measurements of the total cross-section performed by TOTEM at 4 different energies. And then we can just do a parameterization that describes very well the data, and then do this extrapolation, and then the extrapolated proton-proton total cross-section at 1.96 TeV is this value. We use this value here to get the sigma dt, assuming some raw value. We assume this raw value. If we assume a lower raw value like 0.1, since it is here goes as a square and being added to unity, actually the change will be small, less than 1%, that we can add as a systematic uncertainty in the optical point parameter. So we fixed the normalization. We estimated the error band. We did the interpolation to compare the values at the same t values that were measured by D0. This is the D0 published data. And here is the proton-proton extrapolated and normalized data. So we compare shapes. You can see by eye some differences. And basically what is left is to just describe how we do the quantitative comparison, and we do it through a chi-square comparison, taking into account the covariance matrix due to the different correlations between the T-beams, and mostly the main contribution to correlations comes from the interpolation function to compare at the same T values. We also fix the normalization from the optical point, and also we, for the comparison, we fix the B values using the fact that the B values that we obtain are within the uncertainties, and given the theorem from Cornell Martin that says that the ratio of the PP and p-pbar integrated elastic cross sections tends to unity when S is very high, then we do include this constraint here and then calculate the chi-square we get. This is the value of the chi-square we get for the 8 characteristic points that we were comparing, but we fixed 2 constraints, so we end up with 6 degrees of freedom, and the p-value for this 6 degrees of freedom with this chi-square corresponds to 6.1 times 10 to the minus 4, which shows that the difference in the 2 distributions of the sigma dt pp extrapolated to 1.96 TeV compared to the measurement from D0, they differ by 3.4 sigma level. And that's what we observe. So this difference in the sigma dt's we interpreted as a contribution from some conjugation, charge conjugation, odd amplitude contribution. And that's why we say these TeV energies, there is some evidence of this other amplitude contributing. Now, I showed you at the beginning this other measurement that the TOTEM has already performed on the total cross-section and raw values, and how there is a tension between sigma tot and raw values as compared to models that only include Pomeroy effects, and there was already exclusion. This data was taken in different T regions with different detectors, so it's fully independent from the measurement that we are presenting here, so we can combine with the chi-square now these 2 evidences for contributions from odd amplitudes. And then we get overall significance ranging between 5.3 to 5.7 sigma, excluding Pomeroy-only models. So then we arrived to the concluding remarks. We did a thorough data-driven comparison between the TOTEM PP at 4 different center of mass energies with the D0 p-pbar at 1.96 TeV elastic differential elastic d sigma dt. And we found that the 2 d sigma dt's extrapolated at 1.86 from proton-proton data, and the one measured at 1.86 TeV differ by 3.4 sigma. And when we do the combination of this evidence that we get for some contribution from odd amplitudes with the other evidence coming from sigma tot and rho, we get to the 5 sigma level, showing that actually we get like a first experimental observation of the other. This study was already accepted recently for publication. Here is the reference. So thank you for your attention.
Thanks a lot, Professor Carlos. Is there any question, Professor Carlos Avila? I believe it's not the case. No question in Q&A, no right-handed. So thanks a lot once again, Professor Carlos Avila. It's very, very in detail presentation. I guess with these we can then move forward to the next speaker, Professor David Chinellato, which I believe is connected.
Can you hear me?
Yes, we hear you.
All right. Can you
So,
also see my slides?
Yes, we also see.
Sorry, just checking.
Professor David Chinellato is Associate Professor at Campinas State University, where he also took his PhD. He works for the ALICE collaboration, where he took convenership positions on light flavor analysis. And nowadays he's the chair of the ALICE editorial board and member of Physics and Management board. Professor David, the floor is yours.
All right. Thank you very much. Okay, so thanks a lot for this opportunity to be here today and to say a few words about some soft physics highlights from the ALICE collaboration. Now, to get started, I wanted to just briefly explain the mandate of the ALICE collaboration. As you all know, ordinary matter is made of protons and neutrons, and quarks and gluons are always confined within these hadrons. Now, as you think of extreme situations, you can imagine that as you approach a density that is very high in terms of protons and neutrons being clustered together, all of a sudden the limits don't actually matter anymore. And then you have the formation of what we call a quark-gluon plasma. And this is a new state of matter, which in itself is very interesting. However, it turns out that if you want to put protons and neutrons all the more closer together, meaning you increase the baryon density, the net baryonic density, this is very hard to do. Actually, another way of doing it is to just increase protons and antiprotons to a very high degree, meaning that you increase temperature by providing a lot of energy. And that's in fact what we do at the LHC whenever we collide lead nuclei. There too, we achieve a quark-gluon plasma, however, with zero net baryonic density, because you have a lot of protons and antiprotons being created in the end. So that is the extreme state of matter that we want to study once we transition from protons and antiprotons to this melted state of quarks and gluons. And that's what the ALICE experiment is all about. We want to understand that state and how it comes to be and how it can emerge, how it can have properties that emerge from basic QCD. As it turns out, when you collide lead-lead, you form a system that's kinematically and chemically equilibrated. So what actually tells you how the system is supposed to behave is hydrodynamics and statistical mechanics principles. And I will come to that as I show you some of the results, and I will show you these results having those aspects in mind. Now, what do we use to get those results? Well, we have an experiment set up at the LHC, and the experiment, the ALICE experiment, is really geared towards the very high multiplicity environment of a lead-lead collision, and it's geared towards doing particle identification. So some of our main detectors are the inner tracking system. That's a silicon detector made out of 6 layers, and which does not only tracking, but also particle identification via energy loss in the silicon. We have the largest time projection chamber in the world. That's our main tracking detector, as well as it is also able to do particle identification via energy loss. And in addition, also a topological particle identification looking for weak decays. In addition, we also have a time of flight detector, which is able to measure velocity, and combined with the momentum information, this allows us to tell particle species apart at a larger momentum. And last but not least, we also have the V0A and V0C detectors, which are backwards and forward detectors, which are able to not only trigger, but also to provide a multiplicity estimation with which we can select lead-lead events, but also PP and P-lead at low and high multiplicity, respectively. So this is the experimental setup, if you will. And now I come a bit to the results. As I said, if you have a lead-lead collision, we do believe that we have a kinematically equilibrated system. And related to that is the development of flow. Now, when you collide 2 lead nuclei, you form an almond-shaped interaction region, like the one that you see in this cartoon. Now, there are many ways in which this almond-shaped region could emit particles afterwards. It could emit particles incoherently, meaning that each source just radiates in any random direction. Or you could also have a collective expansion, which leads to an azimuthally different emission if you look at different areas with respect to your almond-shaped region. And that second option is, in fact, what we observe. And we can quantify this azimuthal anisotropy by using a Fourier decomposition of particle emission in the azimuthal plane. This is what we do when we calculate the V2, which is the first possible combination which arises from the flow. This is what you see here for protons, kaons, and all the way to helium-3. And in fact, it's actually something that's more pronounced for mid-central collisions as opposed to central collisions. And this is just purely geometry. So everything does make sense here. It's also such that the flow seems to be smaller for a more massive particle, which is again consistent with the idea of a general expansion that is actually based on a common velocity field. It doesn't just stop in the light flavor sector. We've also measured flow in the heavy flavor sector by looking at the zeros, J psis, electrons from beauty decays. And then as we finally move towards the upsilon, which is a very massive particle, we actually see no flow within our very large uncertainties. So everything here does point towards some sort of kinematic equilibration. Maybe it doesn't so much affect the beauty quarks. This is still to be seen with larger precision, but it does paint a very consistent picture. In addition to flow, I wanted to also highlight one particular aspect of the QGP, which is very interesting, and we also measured very recently, which is that it is able to impinge angular momentum on the particles that it emits. Meaning that if you look at K stars, these are vector mesons, and you look at the spin density matrix element ρ00, that's supposed to be 1/3 if you have no preferential alignment of the spin of the K star. This is the case in PP, so that's all fine and nice. But if you look at lead-lead, you're going to see that there is a significant deviation from a third at low momentum, meaning that somehow these K stars are actually getting part of the angular momentum of the system, of the QGP, as it rotates. Now, it's not surprising that the QGP rotates. What's actually quite interesting is that there is a mechanism which imbues the particles that are emitted afterwards with this angular momentum. And again, this is a challenge also for the theoretical field, but we do have the measurement for that. Now, another thing that we learned from this onset of a flow-like behavior is that it doesn't really start only in lead-lead. We've seen also this azimuthal modulation also in p-lead. That's the plot that I show you here from 2013. But since then, we've also done a very systematic study of how it is that this modulation appears not only in lead-lead, xenon-xenon, but then also going towards p-lead and pp as a function of multiplicity. And the very nice thing here is that you see this modulation everywhere. Now, of course, in the heavy ion picture, this is because you have hydrodynamics, you have this expanding fluid. But in PP, of course, these things are harder to theoretically do, but you can try to do them, but there are also alternative explanations. So their PTHIA, for instance, nowadays has a mechanism of string shoving, which is also able to produce this modulation. So here you have also this nice complementarity between two opposing views, say the PTHIA point of view and also the classical heavy ion point of view. These are really complementary, but putting everything in one common perspective is still a challenge that remains to be done from the theoretical side. Still, the data is there for that to happen in the next few years. Now, I mentioned kinematic equilibration, but now I also come to chemical equilibration. And you can do that also when you look at the ratio of identified particle production to pions. For instance, you have here omega to pion ratios that increase as you go from low multiplicity, which is PP and P-lead, to high multiplicity, that's lead-lead. And the ratio kind of stays the same if you just look at lead-lead in general. Only at very peripheral lead-lead with low multiplicities, you see anything different. So this seems to indicate that you have some asymptotic convergence on some values which are really very relevant for lead-lead. And in fact, you can study the identified particle production in the context of a statistical generalization model, and it turns out that you can describe these asymptotic values quite well, also the ratio, the yields themselves quite well, even for particles such as the hypertriton. And in doing so, when you can study this via statistical generalization, you can also look at the properties of the fit that you used, of the calculation of the statistical generalization model, and see if you can understand more about the phase-phase diagram that I was showing you in my very first slide. Turns out this looks very nice. You can see here the temperature versus the baryonic chemical potential and on the x-axis. The data points here come from statistical generalization model fits to various data from many experiments. And it turns out this really looks very much like my sketch on the first slide. And at low mu b, which is where we are at the LHC, it even turns out that the values that you get from the fit are very consistent with lattice QCD predictions. So again, this builds our confidence on what we're saying, that we're studying this new state of matter, because everything points to one concise picture. Now, this is, of course, the lead-lead regime, but if you look at the ratio plot on the left, you still see that there's a large amount of dynamics in the low multiplicity regime. And in fact, this is something that was also a bit of a surprise when we found it, and it also prompted a lot of new theoretical and experimental work to try to pinpoint exactly how this dynamics kicks in PP and P-lead. Now, I don't want to focus on the theoretical side, but let's just think about the experimental part. So many things have been done also by Alice, for instance, transverse activity analyses, ferocity differential analysis, and even effective energy analyses to try and pinpoint what is really driving the strangeness increase, for instance, if you look at the strange particles. And I want to focus only on the third item that I mentioned here. So what's the point there? Point is, let's see if we can use the forward calorimeters of Alice, meaning the 0-degree calorimeters, to measure the energy that was not used in a proton-proton collision so that we can quantify the energy that was actually available at the initial state for particle production. So in doing so, what we define as this effective energy, which is square root of S minus the deposited energy in the forward calorimeters, which was not used, was not deposited in the interaction region. And the main point is, okay, so how can we then look at, for instance, Xi production? Is it such that the available energy in the initial state changes Xi production, or is it just really the multiplicity as you were seeing in the previous plot? And then we came to this very nice plot on the right here. Here you see on the x-axis the percentile of this effective energy estimator. And you have two sets of curves here. You see data points for low and high multiplicity, but regardless of which multiplicity you're looking at, everything is x-axis independent. This means that the initial state energy, the energy that's available there, it's completely irrelevant for how many Xis you're going to produce. Rather, it's really the final state charge particle multiplicity that drives the Xi production. So this is, again, an experimental confirmation of something that restricts where strangeness really has to be produced in these collision systems. I want to also show you some other highlights of, say, soft physics-like measurements that I think are quite interesting. Alice has been doing a lot of things in the anti-nuclei measurement sector. And the point is, we can use the LHC as an anti-nuclei factory. Okay, so we have a large amount, for instance, of anti-helium-3 being produced. We can measure how these nuclei interact with our detector. And in doing so, we can calculate for the first time the inelastic cross-section of anti-helium-3 with matter using different, well, depending on where you are looking at the detector, with different mass numbers. In turn, this is a very interesting measurement because it can also even be used for looking, for instance, for dark matter. Point is, if you have a dark matter signature that might result in anti-helium-3, you want to know how much anti-helium-3 you're going to detect. And for that, you need this cross-section because a model that aims to propagate anti-helium-3 through the galaxy has to have a dark matter source, a propagation term, and also has to know what the probability is that this anti-helium-3 interacts and annihilates. Now, this was done in very many conditions. I don't want to go into all the details, but this I just show you an example plot from a calculation in which the anti-helium-3 dark matter signal was calculated. And the transparency of this signal as a function of the energy of the signal was calculated for both the potential dark matter signature and for a background calculation. But this goes to show is, okay, you have a 50% transparency for your signal. The background actually does change the transparency as a function of energy. This just actually tells you where to look in terms of energy such that you have a reduction of the background and the signal is still there. Okay, so this is how you can maybe constrain, even with these accelerator measurements of the anti-helium-3 cross-section, you can constrain where to look when you want to look for dark matter in astrophysics. Now, last but not least, this is my last highlight. Alice has also been measuring baryon-baryon interactions, and this is a very promising field. For instance, what we can do is we can look at proton-proton collisions that have produced a proton and a Xi. And once these two particles are produced, you can measure their interaction right after leaving the interaction region, provided that they are close enough in phase space. To do that, you actually measure a correlation function as a function of relative momentum for a pair, for instance, proton versus proton and Xi and proton and omega. And as you look at small relative momenta, the peak that you get encodes how these two particles have interacted. And this peak can be readily compared to calculations from lattice QCD, for instance. Turns out that actually the proton and Xi and the proton omega pairs actually interact attractively, which is something very interesting, especially if you're interested, for instance, in calculating a neutron star equation of state. One of the things that is not really very well known is if hadronic neutron stars could actually have hyperons in their composition. If there is an attractive interaction here, that actually has to say something about the equation of state as well. So this is, again, something that could have relationship with astrophysics. Now, there's more to come. I think that Alice has a lot of upgrades, and I want to highlight some of them in a moment. And we will even do omega-omega interactions. But for that, we have to look at things with brand new detectors. And here I bring you to the future. And it does look quite bright, quite literally. We have at the moment a very massive upgrade, which is nearly complete now in Alice. We have replaced the readout in the TPC by a gen-based system. This gives us about a factor 50 in terms of readout capability. We also have replaced the inner tracking system, the silicon system. Again, a big increase in tracking precision, this all for run 3. But even beyond, we plan on replacing again our inner tracking system with the ITS-3. That's a very interesting concept, extremely reduced material budget. It's just a thin sheet of silicon within the acceptance. Everything that is surface has been moved to the periphery. It's all very nice. And even beyond 2030, we plan on actually having a brand new detector, which is being called ALICE-3, which is solely silicon based. And this will buy us another factor of 50 in terms of readout capability. Now, all of this buys us a lot of physics potential. I just want to highlight two very quick things here. One can measure the glow from the QGP, meaning literally the black body radiation, if you will. So we can measure the thermal radiation from the plasma before hadronization by looking at the invariant mass distribution of soft dileptons. This is going to be something very interesting because we usually only access the hadronization temperature. In addition, we plan on getting a very comprehensive understanding of charm production, especially even multi-charm baryons. This will tell us not only how hadronization works for these objects, but also how these objects have propagated in the QGP. So a lot of interesting things to come. Now I get to my conclusions. Hopefully I've convinced you we have a chemically and kinematically equilibrated system in nucleus collisions, but beyond that, Alice has been doing a lot of other stuff. We have advanced a lot the understanding of QCD at high density from PP and PA studies, and even other things that we have been doing are also extremely interesting. And that's not where it stops. In fact, we have a large upgrade program set for the next decade. And I, for one, am really looking forward to what the future will bring us. So that's what I had. Thank you very much.
Thank you, Professor David. Thanks a lot. Do we have any questions? If not, well, I have a question. Actually, I got curious about something on slide 12.
12, yes.
When you measure the progressively lower flow, and then you say that there's no flow for the upsilon. One is just an effect of the higher mass of the upsilon. Is there any other reason behind this for the upsilon that we have no flow?
So there are two things. And it's not, I mean, you see uncertainties and everything, but you see there are two things. First of all, the beauty quark is extremely heavy. So it's not so obvious if it will gain from the collective expansion of the system as it is for lighter quarks. Okay, so that is the first thing. That would be, say, the canonical explanation for what we are seeing here. On the other hand, there's another thing which is also relevant, which is kind of like the mass argument, which in fact would have you believe that even if this object is expanding with the same flow, because of its larger mass, actually the region in which you might expect the flow to be there, even in the same model of hydrodynamics expansion, is at a larger PT. Okay, so in some sense, what this measurement does is, it indicates consistent with zero flow. That's definitely true. But it doesn't yet rule out completely that the upsilon still has some flow at a slightly different momentum or something like that. Okay, so these are these are also considerations that have to be made. But also for this kind of statement, we need to also look into charm and beauty in the upgrade so that we can really conclusively say, okay, how do these objects really propagate? Because our canonical explanation would be mass is too large, they will not equilibrate in the same manner as easily. Okay, but time will tell.
Okay, thanks. I guess I have a question from Professor Michael Albro.
Yes, so thank you, very interesting. So the helium-3 and anti-helium-3, if I saw correctly, they're about the same production cross-section, is that correct?
That's correct.
Understood. You know, when we saw anti-deuterons way back at the ISR, we had a coalescence model where a p-bar and an n-bar were produced and coalesced. Is that model appropriate for anti-helium-3 and helium-3?
Absolutely. So indeed, the coalescence approach is one of the main models with which we describe our nuclei production in ALICE. And there are many approaches. I unfortunately don't have anything here to show, but indeed there are even newer developments in these models which get a lot actually right. Okay. So in fact, one of the things that we still have to struggle a bit with is to put the coalescence model also together with the understanding that the statistical hadronization model works. Okay, so if you will, I was showing this plot. You see, also here I have anti-helium-3 and helium-3, and this works nicely, but the statistical hadronization model doesn't care about, it's not the same thing as coalescence, and depending on the region of phase space, neutrality and everything, they will give you different predictions. It's not entirely clear what is the better option. This is still something for which we need a few more measurements.
Thank you. Thank you.
Thanks, Professor V. Because I have no further questions.
Very good.
Thanks. Thanks a lot.
Thank you. So I guess we can move to the next speaker, Professor Marcelo Munhoz. I believe he's connected.
Stop my sharing.
Hello, can you hear me?
Yes, we hear you loud and clear. So Professor Marcelo Munhoz is Associate Professor of Physics at São Paulo University, where he took his PhD in nuclear physics. Has experience on heavy ion collisions and worked for Star Collaboration, Brookhaven National Laboratory, and nowadays he's a member of the ALICE collaboration. I guess you can go on, Professor, or stop.
Okay, thank you, Felipe. So let me thank the organizers as well for inviting Alice and Alice for inviting me to give this talk. So my talk will be more or less, I think, complementary to what David has presented, since he has focused on the soft probes. I will talk about hard probes. So David has done already a very good job introducing the subject, so that just make a little bit remind you for the context. So we want to study this nuclear matter phase diagram, and to do that, as what we do, we use high energy nuclear physics and nuclear collisions, so relativistic heavy ion collisions, and we can do that in very few places in the world. And the one that I'm going to talk to you about is the LHC, where, as we can see in this chart, is concentrating low density and high temperature. So I will present to you some results of the ALICE experiment that we have already presented, the experiment itself. I will, of course, focus on the results of runs 1 and 2. And I will also concentrate on lead results and on the so-called hard probes that I'll try to make it clear what we mean by hard probes when we talk in this field, and basically heavy flavor and jets. So since we have these two relativistic heavy ion collisions to study this phase diagram of the nuclear matter, of course, when we get these two, we need to understand the dynamics of the collisions. We need to understand what's going on during the collision, using, of course, fundamental theory, using models based on QCD process. But this is a very challenging task, because there are many things going on in this collision. So if we imagine after the collision, we have some pre-equilibrium stage, and then we have many evidence, as David has shown, of this equilibrated system that we call the QGP, the quark-gluon plasma. But then things keep happening, the hadronization, the hadrons keep interacting until we get the chemical freeze out, and then we stop producing new hadrons, but the hadrons still change momentum until they really reach the kinetic freeze out, and that's what we measure in the detector. So we need to take this that we measure and try to infer what happened in the beginning and try to understand the properties of this medium and so on. So it's a very delicate task, and we have basically two approaches. That's why we divided this talk in these two parts, David and me. So we can just look at the global properties of these particles, like flow and the production of heavier hadrons, as David discussed before. So just the manifestation of the formation of these particles in the late stages. Or we can try a more Rutherford-like experiment, let's say, and see if we can identify high energy probes or hard probes that can allow us to do a kind of tomography of this plasma, of this medium formed in the collision. So in any way, we need some reference. So even if I'm concentrating in lead results, of course, we need the proton-proton and the proton-nucleus results to be sure that we are doing this tomography and we are learning new things about this medium. So what hard probes I'm talking about? So I'll show you results about three different quantities, two different hard probes. One is the heavy flavors, so just the production of charm and boson quarks. So the idea is that these guys will be produced at early stages of the collision. We know that from QCD that they should be produced very early when you have a lot of energy at your disposal, and they will leave more than the QGP. So we really expect that they will go through this phase and bring us some information about it. So if we look at the low PT as the flow, for instance, that the view was showing, we can probe with these guys the thermalization for if they thermalize with the QGP and how this process happened. But if we look at the high PT, that's what I'm going to show you. We can learn things about the QGP through energy loss. So the idea is that these quarks are expected to lose energy or less energy, so in a different way than the light quarks, and then we can probe the density and size, for instance, of the medium. There are many particles that we can look at. I will show you some results concentrated on meson D or the open heavy flavor mesons, the meson D results. So one of the most basic things that we can measure in these collisions, one of the first things that you can extract is what we call nuclear modification factor. This is simply the ratio between the spectrum, the PT spectrum of this particle, so how many particles you produce as a function of PT in nucleus-nucleus collisions, divided by a normalized spectrum from proton-proton collisions. So the idea is if this ratio is 1, basically you don't have anything much different from proton-proton collisions. If it gets another value, so you can study, then it's bringing you information about the medium. So let me show you this. Sorry, go. It's not showing, but it's okay. So let me show this result, a quite recent result. Busy plot. Let's go for each element of this plot. So we are seeing here the RAA as a function of PT, right? And the black circles here are is the result for the average value of the 0, the plus, and the star plus. So what we see as a function of PT, that for low PT, this ratio is close to 1, and then it goes down. So we have a suppression. So we have less of these guys in nucleus-nucleus than proton-proton collision as we go to higher PT. And so we do see these heavy quarks interacting with the medium. And the new result actually here is this red crosses, that is the DS mesons. So what is interesting about this result is the fact that we see that although the systematic error is a bit large, we see that they are systematically above the average meson D. So it means that DS is less suppressed than the other mesons. What tells us that there is some very nice dynamics going on between the charm quark and the charm strange that is very abundant in these collisions. So the fact that you have this abundance of strange quarks, it changes the dynamics of and the suppression of these mesons here. And we see that also some model comparisons, and we can see that it's not so easy to predict this behavior. We see that some models predict very well for lower PT, but not so well for higher PT, and vice versa. So sometimes it's good for higher PT, but not so good for lower PT. So it's a very interesting probe to look at. So we can also compare prompt and non-prompt meson D's production. The difference is the fact that when we look at prompt, we are looking at charm quarks production, and non-prompt, it's mesons D's that come from the decay of B mesons. So is a different quark that is generating that meson. So when we look at in this plot, we are looking at the ratio between the non-prompt RAA, the nuclear modification factor, to the prompt RAA. So we see that the suppression is different, right? So it's the non-prompt mesons is less suppressed than the prompt. And this is actually consistent what we would expect from energy loss, because from energy loss, we expect that the bottom, the beauty quarks will lose less energy than the charm because of the meso, because of that cone effect. So this is consistent with this energy loss picture that we have. And if now we go to the DS, that is the new measurement, we see that a similar behavior. When you look at the prompt and non-prompt, they are different. And now we can even go a little further and compare the non-prompt DS with the non-prompt D0, meaning we are comparing the beauty hadrons or the beauty quarks behavior when they are combined with strange quarks and when they are not combined with strange quarks. And when we look then to this ratio as well, the non-prompt DS to the non-prompt D0 as a function of PT, we see again that for the hadron that contains strange quarks, it's less suppressed than the one that does not contain any strange quarks. So as I said, since the DS is mostly coming from a hadron that contains beauty and strange, so this is again an indication of this very nice dynamics between these quarks in this medium. Okay, so another harder probe that we can look at is the quarkonia. So it's based and heavy quarkonia. So it's basically the combination of a CC-bar pair, and this was this kind of particle was proposed as a nice probe for the medium because of the expected suppression via a color screening of these mesons. So we produce the CC-bar, but because of the color-rich environment that you have, these guys can dissociate and you suppress this particle. And also this will be a proportional basically to the volume of this hadron. So as you go higher in temperature, you start suppressing different hadrons, different quarkonium. So this observable can really, the sequential suppression of quarkonium states can really be used as a way to probe the temperature and probe the dynamics of this medium. Of course, life is not so easy because when you go to so high energy as the LHC, then you start producing a lot of these quarks, and then you can have this effect of regeneration of the quarkonium. So these pairs, even if they are not correlated, they can start combining and produce and enhance again the production of these particles, of these mesons, the quarkonium mesons. So let's check some of the results of these particles. So here we see again the RAA, the nuclear modification factor, but for J-psi as a function of PT. We see in two different rapidity ranges. The black is the mid rapidity and the red is forward. And then we see that indeed for low PT, unfortunately I didn't include here the RIC result, but if we compare this result to the RIC result, we see that the RAA is much higher, or is higher in the LHC than in the RIC energies. So indeed we see indications of this regeneration for low PT, where we expect this effect to happen. And this is a stronger or more evident for mid rapidity than forward rapidity. If we now go to beauty, we look at upsilon 1s, same thing, RAA as a function of PT, but then here we see that for the upsilon, this is flat. We don't see so much of the regeneration for the lower PT as we saw in J-psi. And also, if we now look at not as a function of PT, but as a function of rapidity, combining ALICE and CMS data in this plot, and also looking at upsilon 1s and upsilon 2s, then we see that indeed that sequential melting that we talked about is really going on. So we see that the suppression for the 1s is higher than the 2s. And also one thing that is interesting to notice is this, for this higher rapidity, then it seems that the models that we have here predicting or describing the behavior of this data is not so well described anymore. So it's an interesting thing to look at. And as a last hard probe that I like to show you are the jets. So the jets, also the idea is the same, right? You have a hard scattering of two partons. They will, of course, this also will happen in the beginning of your collision, and these guys will go through the medium. So they can be an excellent probe for the properties of this medium as they go through, right? And so the strategy is to look to any modification of the jets, of these jets in nucleus-nucleus collision compared to proton-proton collision. So as you can imagine, in nucleus-nucleus, we have a big challenge looking at jets because of the background. So it's very hard to subtract the background for this observable. And on the other hand, we want to go as low as we can in PT and as large as we can in R, because we really want to, because these are the places, or these are the the phase space where these effects will be larger. And if we go to large R, we can, for instance, include back any spread of the jet that happens because of the medium. So here again, we go back to our nuclear modification factor. So the REA is a function of T for jets. And what we show in these pictures is I think, if we the green dots show the jets when we subtract the background using the area-based method. So we just compute the mean, the average density of particles in the event, and you multiply by the area of the jet, and you subtract to take out the background. And the blue dots shows the same thing, but when you use machine learning techniques to subtract the background. So we see that using these techniques, we can go lower in PT. That is a nice thing. And the lines here just show different fragmentation models for training the machine learning. So it shows that the bias is not so large for this technique in this case. So it's a very nice result for going further in these studies. Let me just show you the comparison of this result with some models. Oops, too fast. So here, these are the models that we compare the data, and just to highlight that you see that how important it is to go to lower PT, because here we have a good discrimination of this of this result. So just the last thing, if we can also look at the substructure of the jets to see if the inner part of the jet changes in nucleus-nucleus collision. So here I'm showing just one result. It's called the groomed substructure using the soft drop technique. So the idea is to identify the most significant splitting of the fragmentation of this jet, throwing out softer radiation using these cuts. So here in this light blue are just a schematic example of soft radiation that is we get rid of it, and then we get this splitting, and then we can look at the ZG variable that is just the fraction of PT carried by the subleading jet. So from these two branches, the one that has less energy, you divide by the total PT of the two branches. And we can look also to the distance, the angular distance between these two branches of the two jets. So it's a very nice technique that was used in PP, and then we using here in LED as well. So here is the result for the ZG. So we see for lead and proton-proton central collisions, applying some cut 0.2 and 0 for beta in the soft drop technique. And what we see, and also this was tested for all the different parameters as well, different values of these parameters. And we see that this is very flat. So we don't see much difference in this observable in lead. However, when we go to the angle difference between the two branches of this splitting, then we see when we do the ratio between lead and proton-proton, then we see a difference. Then we see that in lead there is like a predominance or enhancement for more narrow jets than in proton-proton. So let me finish. I'm sorry, I apologize for the time, but I hope I have convinced you that we have very nice evidence for hard probes interaction with the medium and the potential to extract medium properties from these observables. Also, I hope you notice that these measurements are getting more differential and precise, overcoming this very challenge that we have in heavy ion environment. And as Davi mentioned, Alice in run 3 and 4 will have a much higher rate of data taking. So we expect to go even more differential and precise in these measures. So thank you very much. And if you have any questions, please send me a message. Feel free. Thank you.
Thank you, Marcelo.
Thank you, Marcelo. Do you have any question? Oh, we have a question from Luciano. So Luciano is asking, are there results about the ratio D sub S over D, or even D star over D, as a function of the multiplicity density of charged particles measured in the central rapidity region, dn d eta, with eta equals to 0, usually taken as a measure of the size of the system? Maybe for I guess you can chat.
Yeah, I will not remember from top of my head exactly what happens, but yes, we do have results as a function of multiplicity for these particles. But yeah, I can point you, if you write to me, I can point you to the results, to the plots, and you can check it.
Thanks. Do you have further questions? I guess no. So once again, thanks a lot, Marcelo.
Thank you.
And I guess we can move to the next presentation, which is from Douglas Perry, which I believe is also connected.
Hi, can you hear me and see me?
Yes, so Douglas is an associate scientist at FNAL with research topics including silicon tracking, dark matter, TOP, and Higgs physics. He also held positions at University of Illinois and took his PhD in Notre Dame. He's a member of the CMS collaboration, actively working on B2G analysis, and contributes to the R&D of the phase 2 upgrade, as well as he leads the commissioning of the forward pixel detector at CMS. Douglas, the floor is yours.
All right. Thank you for the introduction, and thank you for the invitation to this conference. Unfortunately, we all can't be in person. So this is going to be a pretty extensive talk, but hopefully give you an idea of what we're doing at the CMS detector. The CMS detector is one of the two general purpose detectors at the LHC. And I think the primary highlight here, which is important to focus on for this talk, is the high granularity of both the pixel tracker and outer tracker, and the ability to pair that high granularity with the calorimeter systems here in green and yellow, and also the muon chambers. This enables us to use a technique called particle flow, where we're able to track with high precision charged particles emerging out from the central collision point from proton-proton collisions at 14 TeV. So this talk was asked to focus on the latest Exotica results released from CMS. CMS produces a lot of different Exotica results, so many that I couldn't fit the 20 or so most recent results in a single 15-minute talk. However, given my background and expertise, I do a lot of work involving top quarks, so I decided to focus on the latest analyses involving tops inside the final state. So these analysis includes supersymmetric tops, leptoquarks, heavy resonances, which to K-to-top objects, and vector-like quarks. And a lot of these searches where we have very heavy objects, which to K-to-top quarks, that result in a detector signature called a boosted top quark to K, which we'll touch on in a second. You can see from the integrated luminosity, all of these analyses use the full run-to data set, which is the data collected in 2016, 17, and 18. And 4 of these analyses are so new that they don't even have preprints on archive yet. So if you just do a quick search on Google for the pass number, you can find these analyses on the CERN document server. So the first thing that I'd like to discuss is, since we're talking about top quarks, the top quark decay. A top quark decays primarily into decays into 2 objects, which is a W boson and a B quark. The B quark decays into a displaced jet called a B jet, and the W boson can either decay to a lepton and a neutrino. The lepton here in this case is fairly easy to detect, and the neutrino passes through our detector undetected, or the W boson can decay hadronically to 2 light flavor jets. The top primarily decays via the hadronic chain to decay channel about 67% of the time, and the leptonic channel about 26% of the time. As the objects producing the top quarks get heavier and heavier, the spectrum becomes more boosted and more collimated. So the lepton is now closer to the B jet, we're making it harder to identify. And these three separate jets merge into a single top jet. Identifying these merged top jets is a critical feature of CMS, which is being used more and more commonly in analyses that relies on the high granularity of the pixel detector and tracking detector. So this is applied to both top quarks, which we'll see here extensively used in this analysis, and also jets arising from the Higgs boson and W boson. In all three of these cases, we frequently use a variable called soft drop mass, which Javier presented earlier, where this is the groomed mass of the jet, and this mass should be near that of the mass of the originating particle. So here you can see the green mass of a W jet is around 90 GeV. Likewise, we use a variable called n subjettiness. You can think of this as a fitter that describes the likelihood of a jet having either one or two subjets or two or three subjets. So you can see an example of this here, where QCD, which is light flavor and doesn't have substructure, we have a very high fit parameter here. But as we have real substructure inside this top jet, the n subjettiness gets pushed to lower and lower values, which is which says that the larger radius jet is consistent with having three cores. So with that in mind, I'll get to the analyses. So the first analysis that I'd like to talk about is the combined top score or stop search. This is really a tour de force of an analysis. It includes a Dielectron channel and a single lepton and all hadronic decay channel. So it's actually three analyses in one. The hadronic channel makes extensive use of both top and W tagging, where the single lepton channel has a large background from what's called lost lepton. This is where you have two leptons in an event and one of them is lost, creating a fake MET. In these channels, we have a dedicated multivariate technique to identify those events. Additionally, we use ISR and soft B tagging to identify events inside the SUSY compressed scenario, where there's a small mass difference between the stop and the neutralino, or stop and charge eno. Likewise, the third analysis is the Dielectron channel, and that makes use of the specialized variable called transverse mass, which is similar to the transverse match, which is typically used for a W boson search. But here, since we have two neutrinos or two escaping objects inside the event, you look at all the possible different combinations for calculating the transverse mass, and then take the minimum of them. This analysis is really needed to exclude phase space inside what's called the top quarter limit, which is again from compressed scenarios where there's a small mass difference between the between the stop and the neutralino. This analysis is also nearly identical final state to a TT plus dark matter search, so it's also capable of setting limits for that model. So the stop search is heavily reliant on identifying W and Z jets. So we use they use both resolved and merge algorithms here. So here you can see the efficiency for identifying jets coming from top quarks. And you can see the result in green starts to become more and more efficient as you pass the 200 JeV point. And then as you pass the 400 JeV point, all these resolved jets become merged into a single large radius jet. Likewise, the same analysis uses a similar technique to identify W plus jets, and you can see that performance here. Again, this analysis makes use of the ability to tag soft B jets. These are jets which are generally around 20 GeV and have a displaced vertex. 20 GeV may not sound soft, but this is actually the minimum energy a jet needs to have in order to be detected by CMS. And again, the two lepton channel uses a variable called MET significance or S to increase the sensitivity of analysis. Here, what this S variable does is it decreases the probability of identifying events with fake MET. So here, when you can have detector effects or misreconstruction that results in MET, which is not actually there, and this parameter can categorize that. So you can see the parameter S here, and then in events where you have no real MET, you have this chi-squared for the number of degrees of equals 2, telling you that these are events with likely not real MET. This is a very complicated analysis, and the full combination has over 266 search bins, which you can see inside the backup slides, but I'm going to skip to the final limits here. You can see on the left-hand side, the calculated exclusion limits for the top corridor, where the vertical axis is the neutralino mass, and the bottom axis is the stop mass. And you can see in this compressed scenario, we exclude the full phase space. Likewise, you could see the expanded exclusion for the full combination here on the right side. The driver of this exclusion is the zero lepton or the all hydrogenic category here in red, and there's some support from the one lepton category. What's very interesting to note is that the two lepton category is fairly weak, except it's 100% responsible for excluding the phase space inside this top quarter region. The overall exclusion limits for this is excludes the 700 JeV LSP for 1,150 GeV stop, and then for the Chargino scenario, we can exclude up to 1.175 TeV for massless LSP. The exclusion limits shown here are just for the stop to top neutralino, but you can see the other two sets of exclusion limits inside the backup slides. Like I said, this analysis is also capable of doing dark matter limits, which you can see here. Here we can exclude a simplified dark matter, either scalar mediator or pseudoscalar mediator, up to masses of 400, 420 GeV. Then the next SUSY search is a RPV SUSY stop search. In this case, the LSP is no longer stable, and so you have a very complicated cascade decay, which results in very high jet multiplicity. So in this event, you have two top quarks here, and then up to an additional 6 jets inside the event. We use a neural network in order to differentiate our signal from the p-pbar background plus jets. There's 24 different categories where we score the neural network output, and we train this neural network such that we can preserve the n-jet shape inside the different bins. The n-jet distribution is what's used for the final state, for the final calculation of the limits. So it's very important that this neural network not alter that shape, and we were able to achieve that with adversarial training. So you can see here the final combination of the n-jet spectrum. You see very good agreement between the data of Monte Carlo. Here you can see what an RPV signal would look like at 450 JeV, and also a stealth SUSY signal at 850 JeV. And you can see it's fairly well modeled with a slight excess in the 11 jet bin. This is actually the combination of over 16 different categories, and you can see the n-jet distribution for the 2017 data set, and you can see the adversarial training is doing a very good job of generating the n-jet shape. Due to the small excess here, the limits aren't nearly as powerful, aren't as powerful as you would expect. However, you still get fairly strong limits. The RPV stop is excluded between 670 JeV, and the stealth SUSY model is excluded between 300 and 870 JeV. You can see there's the observed limits do worse than expected, and you can see the p-value plots inside the backup slides. The next search that I would like to talk about is a third generation leptoquark search. In this case, you can either have pair or single leptoquark production, with a leptoquark either decays to a top quark and a tau particle, or a B quark and a neutrino. In both the pair production case or single production case, you always have the top quark, tau, and neutrino, where the B jet is optional for the pair production case. Type 1, type 2, type 3 top tagging are used to identify the top jet. Again, type 1 is where everything merges to a single jet. Type 2 is where the W boson merges to a single jet. And type 3 is the traditional resolved approach. And due to the nature of the final state, you expect large separation between the top jets, the narrow hadronic tau decay, and the B jet. This hadronic tau is very difficult to model from simulation, and so that's modeled extensively using data. Here we create a dedicated control region to model the hadronic tau fake rate from data. And we model that by removing the p-pbar and Drell-Yan backgrounds, which can have actual real taus in there, and primarily use W jets and QCD. So 90% of our control region is dominated by fake taus, which we then use to estimate the fake tau contribution inside our signal region. You can see the 4 different signal regions here. The 2 left plots have the high sensitivity, where the top jet is fully merged. Here's we find one B jet inside the event, and in the bottom plot here we find more than one B jet inside the event, where this is our most sensitive category. And then for the resolved category, you can see that there's a lot more background, so it's less sensitive to the signal. Here you can see the leptoquark limits. There's been a renaissance in leptoquarks since the B decay anomalies were observed at Bell and p-pbar. Those anomalies generally favor a phase space here in this gray region, and the combined search excludes up to this black line here. So the dashed line is the expected, the solid line is the observed, and we can exclude third generation leptoquarks up to 1.3 and 1.65 TeV for the k equals 1 and k equals 0 coupling scenarios. We also exclude a scalar leptoquarks up to 0.95 TeV, which are not shown here. The next search is a B to TW search. This search here is looking for, again, a boosted top quark decaying to a single jet, accompanied by a W boson, which decays leptonically. We use a specialized algorithm here. Instead of saying we want a single large radius jet, a fixed radius, we use the HOTVR tagger, or heavy object trigger with variable radius. This enables the characteristic jet radius to change with the boost of the object. Additionally, we use a deep neural network to identify B subjets inside this large radius jet. And the presence of a lepton here enables the search to exclude limits down in this very low mass region, down around 700 G EV or so. And the invariant mass of this lepton here, and the top jet is used for the final state of observable. You can see the observed distributions here in MTW. There's very good agreement between data and Monte Carlo, and this search can rely 100% on the simulation in order to model the backgrounds. The one point where we do use data is to generate a transfer function for the top tagging mistag rate, and then this is then used to model the shape and normalization inside the signal region. You can see the limits extracted from this analysis here. you can see that there's a slight excess here around 2.2 T or V or so, and this is a 2.2 sigma higher than expected. But when you take into account all the mass bins where we search, the global significance is less than 1 sigma. Again, you can see a sharp transition here where the single lepton analysis really shines because the all hadronic channel does not have sensitivity to that low mass. The B star is excluded to masses of just above, just around 3 TeV, depending on whether you use left-handed, right-handed, or vector-like couplings. The next search is a search for a heavy W prime boson. Again, here we're talking about very heavy, generally between 1.5 and 5 TeV, where here the W prime boson indicates to either a T quark and a vector like B.
Sorry, Douglas.
Yes?
Sorry, but just to inform, I believe you are already 5 minutes away from the
okay, well then let me just skip to the distributions here. Again, this is interesting because we use an ABCD method for extracting the QCD background inside the signal region. We get very good agreement inside the results, and we're able to exclude up to 3.2 TeV. And the last search is the single vector like T search. Again, this is very similar to a mono top dark matter search. What's interesting here is we modeled the vector like top at 4 different widths, which enables us to do limits for 4 different widths, which results in a 2D limit plot where we can get a generalized top plus mat search to exclude various different vector-like top quarks for a variety of different widths. And that concludes my talk. You can see a summary of all the different limits produced here on the final slide, and I won't go into repeating them as I'm already over time. Are there any questions?
Thanks a lot, Douglas. Doesn't seem that we have a further question, but in case, I suppose people can get in touch straight with you by email, for example. Mm-hmm. But thanks a lot for your very detailed talk. I guess we can move forward to Professor Tetiana Hryn'ova. I believe you can, you're the one who's sharing.
Hello, can you hear me?
We hear you very well.
Okay, can you see my screen?
Yes, we see you. So just to introduce you, Professor Tetiana Hryn'ova took her PhD in SLAC 2006 to 2008. She's a staff at LAPP in the beautiful city of Munhoz, where she leads the Atlas group in that institute. She works on the search for new phenomena in the final states with leptons. She also participates in the upgrade of the electronics of the Atlas colorimeter for the high luminosity LHC and works for the Atlas trigger system. Professor Tetiana, I guess you have 15 minutes. I'm going to stop.
Thank you very much for this very kind introduction, and I really enjoyed all the previous talks, and I hope to be able to fit into this wonderful pattern. So, greetings from Munhoz. I will talk today on searches for new physics at Atlas. So why do we need to look for physics beyond standard model? Following the discovery of standard model Higgs boson in 2012, standard model is complete and self-consistent. But there are many aspects of standard model which don't have explanation. We don't know the origin of dark matter or how to accommodate gravity. We don't understand why Higgs is light and what is the solution of hierarchy problem. We don't understand why there are 3 generations of fermions. And there is a whole plethora of theoretical models which try to address different questions, some of these questions, but there is no theory which addresses them all simultaneously. Thus, we are in I would say unique situation in the last 10 years where we are searching blindly because we don't really know what we should expect to find. So how do we search? What we can search for and what we do search for are any deviations from standard model predictions. So we can search in two ways, either in direct observation, looking for new resonant or non-resonant structures, and this will be the subject of this talk, or in indirect observations, where we look for discrepancies in rate of rare processes, coupling measurements, etc. And this will be presented in the talks by my colleagues which follow. The focus of this talk will be a selection of recent atlas results, because there are too many to cover in 15 minutes, which will come in three categories: signature-based searches. Then I will focus on searches where Higgs is used as a gateway to physics beyond standard model. And then I will touch upon searches which are relevant to flavor anomalies discussion. And all the analysis presented use full run-2 dataset collected in 2015-2018. So first signature-based search, which I will talk about, is a search for diboson resonances in WH channel. Such resonances are expected in models with extended gauge symmetry or minimal working technicolor or little Higgs or composite Higgs models. The analysis is basically a bump hunt, but because we have a diboson system where we are looking at diboson decay products, they're typically collimated, and if you're looking in hadronic channels, there could be large R jets which have a substructure. So what I will look in for this particular analysis is W prime decaying into Higgs and W, where Higgs decays in a pair of B jets and W decays into lepton plus neutrino. So Higgs decaying into B jets could be either resolved, then we can reconstruct two B jets, or merged, where we reconstruct a large R jet. So to do that, we would need to do Higgs tagging, where we have one or two big tagged variable radius track jets. Here you can see the result of this analysis, where we have number of events versus the function of WH mass. And as you can see, the data matches Monte Carlo prediction very well. We observe no excess, which allows us to set cross-section limits, which are less than 1 inverse femtobarn at masses above 3.7 TeV. Moving on, I would like to discuss monojet search, which is a golden channel for dark matter. The search is very simple. It requires one jet, high PT, above 150 GeV, and a lot of missing transverse energy, 250 GeV, and it vetoes leptons and photons in the event. Why do we call it a golden channel? It's just because there are so many models it can cover. It can we can look using it for dark matter production in association with ISR jets, or supersymmetric particles in compressed scenarios, or new scalar particles in dark energy inspired models. This search has backgrounds coming from from Z decay into neutrinos or W plus jets, TT-bar and single top. All of this we can control using control regions, and we also use higher order QCD and Electroweak corrections to get better values for them. As you can see in this distribution of PT recoil, so number of events as a function of PT recoil, we have an excellent agreement between data and standard model prediction. This is really a precision search with background uncertainty of only 1.5 to 2.5% across the signal region. So the results of this analysis are in parts a model-independent cross-section on model-independent limit on the visible cross-sections, which is in the range of 730 femtobarns to 0.3 femtobarns. And we can also use this analysis to set 95% confidence level exclusion on Higgs to invisible branching ratio of 0.34 observed. And with this, I would like to move to my next topic, which is probing BSM phenomena with the Higgs boson. So as I said just before, the important thing is to look for Higgs invisible decays. Why do we do it? It's because these decays are very small in the standard model. Only 0.1% of the Higgs total branching fraction. And any dark matter to standard model interactions mediated by Higgs boson would lead to enhancement in these decays. So actually, one of the ways to study it is to look at standard Higgs production as a standard model with Higgs decay into invisible and see what we measure. And for this analysis, which I would like to present you here, we have done it for the TTH channel, where we looked for MET plus TTH, and in vector boson fusion channel, where we looked for MET plus 2 jets. And you can see on the top right plot the results which we obtained. In the first two columns, you can see here the results for run 2 TTH and VBF, and you can see that VBF has much more constrained results, the combined result for run 2, and the combination of these results with what limits which we had in run 1. So the total combination from various Higgs productions in run 1 plus run 2 allows to constrain this Higgs to invisible branching ratio up to 0.11 observed, which is very similar to what is expected. I must say that this result could be improved even further if we do global Higgs coupling combination limits, and then we constrain it up to 0.09. And this might be discussed by the previous speaker. In any case, we can use these combination results and translate them into spin-independent dark matter nucleon scattering cross-section limit in Higgs portal scenarios. We assume that there is interaction between dark matter and nucleus mediated by Higgs exchange. The results of this can be seen in the plot on the left, where we show the Higgs portal model limits for scalar WIMP in blue and Majorana WIMP in red. This is based on our results, and we also compare them to the limits obtained, which could be reached by other experiments such as dark side here in orange and xenon one tone shown in blue. Moving on, I would like to show you a slightly more complex analysis where, in addition to the Higgs produced on the VBF channel and missing transverse energy, we require an extra photon. This paper has many results, and here I show you only one, where this VBF produced Higgs decays into a photon and a dark photon. So what we do here is that we study the transverse mass of photon plus missing transverse energy combination, and we split it into two MJJ categories, below and above 1 TeV. And we check we compare data to Monte Carlo prediction, where in Monte Carlo we expect our main backgrounds from Z gamma plus jets and W gamma plus jets. We control these backgrounds from the control regions. Here on the top, you can see the results we have obtained for MJJ below 1 TeV and above 1 TeV with the control regions, and you can see that everything is very consistent with 1. So no excess is observed, and we can set limits on the branching fraction of the standard model Higgs going to gamma dark gamma at 0.014 observed. Now I move to exotic Higgs decays in the final state of 2Bs plus missing transverse energy. We are looking here at associated production of Higgs and Z boson, where Higgs has a cascade decay in the end, decaying into a pseudoscalar A, decaying to BB pair. So we can do selection here requiring Z going to a pair of dileptons, and this pseudoscalar decaying into 2 jets, which are very soft and very low mass, below 120 GeV. We require only 1 B jet, not 2, to increase signal efficiency. And we also require some missing transverse energy. Here you can see the results. So we are looking at dijet invariant mass as our main invariant analysis variable, and we do combined fit of signal regions and control regions here. Again, you can see that we have no excess, and we set limits for various values of NA and neutralino masses here. Moving on to the next analysis, which I would like to show you, these are still exotic Higgs decays, where Higgs decays to a pair of pseudoscalars A, which in turn decay either to BB or to mu mu. In this analysis, we can exploit the excellent dimuon resolution to improve the mass of BB via kinematic likelihood fit. So this likelihood function is actually used as one of the selection variables. We require mu BB state to be consistent with the Higgs mass, and we require very low missing transverse energy in this event. We train a BDT to be as a function of dimuon mass. So there are actually 12 independent BDTs, which helps us to separate signal from the Drellian and p-pbar backgrounds. Here you can see the results, so number of events as a function of dimuon mass, and we have a small excess at 3.3 sigma local, 1.7 sigma global observed at mass of A of 52 GeV. So as you can see, you can also see it on our limits here, and so the limits we obtained are in red, and they're compared with limits we had with previous 36 inverse Munthaman analysis shown in blue. Now I would like to discuss even more exotic Higgs decays. So we still have associated production with Z, but now Higgs decays into two pseudoscalars which are very light with small couplings, which makes them long-lived. So they decay each into pair of B jets, but now these jets do not come from the interaction point, but they come from displaced vertices. So this analysis uses slight radius tracking and displaced vertex reconstruction. And the selection variable in this case is the number of the displaced vertices, as shown on the plot on the left here. And you can see from our results again, we have no excess, and so we set limits as a fraction, as a branching fraction, as a function of mean proper lifetime. And the results of this analysis shown in the middle here with Z plus H displaced label. And you can see that they fit very nicely between our previous results with VH prompt analysis and Higgs displaced analysis, where we had decays in the muon system. So we now can cover a full lifetime range. Now I would like to move to searches which are relevant to flavor anomalies discussion. As was mentioned by the previous speaker, there are lepton flavor universality tensions observed in B going to SLL and B going to C-tau new decays, which could hint at BSM physics involving new bosons or leptoquarks, which preferential coupling to third generation standard model fermions. So these B decays are actually connected to B to SLL and B to C-tau new through crossing symmetry. So they could be, they could indicate the presence of new phenomena such as heavy Z bosons or leptoquarks, or maybe RPV SUSY. And I will show you atlas results in these areas. So the first one is the leptoquark searches, as were a bit presented already by the CMS speaker. So here we could look in three potential channels. One is a pair production, another one is a single leptoquark production, and the third one is the T channel, and I will focus on the pair production. So for the pair production, we look at events with high PT objects in final state, such as two jets or two leptons, so a charged lepton and a neutrino. And what is shown on the right are our recent full run 2 results, which target leptoquarks and TOPS quarks in the final states of B jets, tau leptons, and MET. The results are actually shown in orange here, and on the top plot we can see the limits on the third generation up type leptoquark decaying to B tau, and in the bottom you can see limits on the third generation down type leptoquark decaying to T tau. And you can see that this results obtained in this direct search are nicely complemented by reinterpretation of our SUSY searches for stop zero lepton channel shown in dark blue here, and the bottom zero lepton channel here shown in orange. In general, our limits reach 1.25 TeV at the branch fraction of around 50%. And as I mentioned before, so what is interesting is the third generation. So one of the interesting channels to look at is, of course, a search in tau new final state. So here we probe MT spectrum for a very wide kinematic endpoint. So detector effects and calibration are particularly important here. So we select on well, high PT tau, reasonable tau, but a lot of MET because we have MET trigger requirements, and we do electron plus mu on Vito. So the background is W to tau nu coming from simulation, while jet background is data driven. You can see the results on the right here, again, number of events as a function of transverse mass. The tau nu system, and you can see that the data again matches Monte Carlo prediction very well. So because no excess is seen, we set limits on the cross section, which reach approximately 1 femtobarn above 3 TeV. In addition to the targeted searches, we also did BSLL contact interaction search, which is fully B anomaly inspired. So because B factor is C discrepancies in B to KLL final state, we thought of looking into the same final state. So our selection is 1 or no beta jets and 2 leptons of opposite charge and same flavor, either electrons or muons, and large invariant mass. And the backgrounds come from Z plus jets and TT bar, which we control through the control regions. And so this is one of the signal regions in the search. This is 2 electrons plus 1B region. And you can see that we have slight access. This is only channel which has slight access corresponding to 2.6 sigma local and 1.5 sigma global significance, which is very small. So this allows us to set limits on this contact interaction scale to be lower than 2 TeV in the electron channel and 2.4 TeV in the muon channel. This is way below the values which are favored by B anomalies. We expect something interesting around 30 TeV. So to summarize, I have presented highlights from a broad program of searches for physics beyond the standard model at the ATLAS experiment, and you can find more information in the links here. We have no large deviations from standard model observed, but we have vibrant activity on the mature Antu data set, which will continue to produce results in the months to come. We develop new innovative techniques and practices for ANS3, which we expect to start early next year. And we hope that the discovery could be around the corner. Thank you very much. Do you have any questions?
Thank you, Professor Tetiana. Do we have questions? That seems to be the case. So thanks a lot for this very detailed presentation. And I guess we had scheduled a coffee break, but I would propose to skip this one and move ahead to the next speaker.
We have to go ahead because the time is too late.
Yes. So let's move to the talk from Professor Evgeny Soldatov. I hope you got your name right. I'm sorry. You talked to us about Electroweak and top measurements at Atlas. Professor Soldatov is Associate Professor of Physics at Moscow Engineering Physics Institute. He works mostly with experimental high-energy physics and data analysis, as well as Electroweak and the standard model. He's a member of the Atlas experiment and deputy team leader of his institutes. Professor Soldatov, I guess you have 15 minutes haven't stopped.
Can you hear me and can you see my slides?
Loud and clear, yes.
Okay, thank you for kind words, and really I would like to thank organizing for inviting me. So it is a pleasure for me to tell you about the Electroweak and top measurements and in Atlas. Yeah, and I will start with a couple of words about Standard Model. Standard Model is extremely predictive theory since its inception, which successfully passes precise experimental tests for about 50 years. And after the discovery of Higgs boson, Standard Model measurements have two main goals, which are the following: to validate Standard Model in new energy regime and improve precision of known Standard Model parameters, and to test for new physics contribution via indirect search, anomalous couplings, and etc. And the Electroweak and top physics have a great potential in both of these goals. Theoretical predictions for most of the processes can be calculated with quite high precision. A lot of rare processes predicted by Standard Model were the loop contributions. So, for example, for new physics particles, this process can become sensitive tools to probe for the new physics models. A lot of analyses were published by Atlas on these topics of Electroweak and top physics, and I will focus on several recent ones. Okay, so let's start from top physics and with very interesting analysis. So as it was mentioned several times today already, there is a clear deviation of experimental result from the Standard Model prediction in rare decays in B physics field. In other words, there is a possibility of the violation of the lepton flavor universality. Not surprisingly, that we are thoroughly checking other places where this LFU can be probed. This analysis is the first LHC test of LFU in W boson decays. The previous result from LAPP had a deviation of 2.7 sigma from Standard Model. For this analysis, the p-pbar events with W boson decaying leptonically were used. For this ratio for the numerator, we are using W to tau nu with subsequent decay to muon. And the denominator is direct decays of W into muon mode. So electron mu final states and mu final states were used here. To distinguish events of this numerator from denominator, the tau lifetime information was used here. It was done through the transverse impact parameter of the muon. This impact parameter was calibrated using the TMMU event selected in the invariant mass window, the lepton invariant mass window. Normalization of the main background, which is from Z to mu plus jets, was taken from the data control region, and the data-driven method was used to estimate the background of prompt muons, not from W. Okay, here you can see the most interesting distributions, which are for this transverse impact parameter, D0, for the electron, for the EMU and mu final states. And the result is here. this result is in agreement with the standard model within 1 sigma. You can see it from this, for example, plot on the bottom. And this is the most precise measurement of this ratio for tau to mu to date. And actually, it has been published in the Nature Physics just yesterday. Okay, now moving to the measurement of joint for top production, which is a rare process which is not observed previously. Its cross-section is sensitive to the properties of the top quark coupling to the Higgs boson, to the hypothetical new particles, and to various 4 fermion couplings. And it can be, the interpretation can be done in the context of the effective field theory framework. This measurement actually has 2 parts of different final states. The 2L-SS3L final state. So this final state contained 2 leptons with the same signs or 3 leptons. This measurement was already published and used here just for combination. Here is the link. And 1L2LOS final state, which is 1 lepton or 2 leptons with opposite signs, will be considered here. So the main feature of this analysis is the smart categorization into the different regions according to the lepton and jet multiplicities and different beta requirements. These categories are used as signal, validation, and control regions. You can see the configuration of these regions for different final states here on the bottom. And the main background is from TD plus jets of different flavor, and you can see its contribution, relative contribution in this picture on the bottom right. Okay, a multivariative analysis is performed here in the signal regions to discriminate for top signal from the background. The modeling of all input variables was checked. There is an example of one of them, sum of beta scores. More you can find in the backup slides. And the results here for this final state is that the observed cross-section is in agreement with the prediction at an alone order. And the combination with this 2L-SS3L final state gives us the cross-section which also agrees with the standard model. You can see the combined result here on the right, but it is in agreement within maybe 2 sigmas, so some tension exists actually here, and the observed significance for the combined result is 4.7 sigma. Okay, so moving on to the next measurement, the TTZ production process provides the direct access to the neutral coupling of the top quark to the electroweak gauge boson. The deviation of this coupling from standard model can come from new physics models. For example, in this measurement, the final states with exactly 3 or 4 isolated leptons were used. Prompt lepton backgrounds are estimated from Monte Carlo with normalization derived from data in WZ and ZZ, WZ plus jets and ZZ plus jets control regions. The fake lepton backgrounds are estimated with fully data-driven matrix method. Here you can see the yields, the event yields from the signal TTZ and from different backgrounds. And moving to the results, you can find here on this slide. So the measured cross-section is in good agreement with prediction at NLO accuracy. And also the differential cross sections were measured here. For example, there is a differential cross section versus Parton level PTZ or Parton level YZ. More differential cross section measurements are in backup, and the signal strength, the combined one is 1.19. Okay, so now we change a bit the topic to the Electroweak measurements, and I'll start from the full lepton differential cross-section measurement here. Several interesting sound model processes contribute to this final state, actually, including even Higgs boson. Also, there is a possibility of additional contributions from beyond the standard model physics. The analysis considers really all four lepton final states with leptons not from hadron decays, and the main background and the main background is from the processes with leptons from hadron decays. Background estimated with fake factor data-driven technique. Fake factor is measured in special contour region in data enriched in non-prompt leptons. The dominant uncertainty here is a statistical one. Next one comes from the background estimation. You can see it from the plot on the right. So the red one is the data, the contribution of the uncertainty from the statistics, and the next one is orange, and the total one is in black. Moving to the results, you can see that for all the categories, the agreement, quite good agreement with prediction observed with Sherpa and Pohek and MEPhI. And also we have measured the branching ratio Z24L, and this quantity is also in very good agreement with standard model prediction by Pohek. Also, the differential and double differential cross-section were measured. Here I am showing one of the interesting ones, the invariant mass of first and second leptons. And you can see also the agreement is observed. And finally, the EFT interpretation was done. You can see it on the right. All parameters were constrained. In general, the observed limits are compatible with the expected ones. Okay, so another measurement I want to discuss here is WW+1 jet differential cross-section measurement. So one of the main motivations of this measurement was the EFT interpretation, actually, since the configuration with one jet and more has a relatively larger sensitivity to EFTs versus zero jet case. Here the final states with full lepton decay modes were used. Leptons should be different flavors and opposite charge. Main TT background was estimated using contour regions, and Drell-Yan Z-jet background was estimated using Monte simulation and checked in the validation data region. Integrated cross-section, as you can see, in a good agreement with matrix with the matrix prediction. I believe it is on NNLO accuracy. Okay, here are some main systematic sources, and also we have measured the differential cross-sections. Here you can find one versus invariant mass of electron and muon, and finally limits on animals triple gauge parameters, coupling parameters were set, shown in the in this bottom table. And moving on to the last study I'm going to show today. In some model, this gamma-gamma to double-double process proceeds through 3 linear and quartic gauge boson interactions. So it is really extremely sensitive to anomalous gauge boson couplings if we can select this process. In this analysis, only lepton decay modes were used. The interaction vertex is reconstructed from 2 leptons in the event LAPP-1 and LAPP-2. The beta of ID tracks, except tag leptons inside a small window around this vertex, is used for exclusivity selection. This is the main feature of this analysis. And this NTRK is the number of tracks, except these tag leptons, in this window. And actually the backgrounds from Drell-Yan and from QQ to WW are constrained from contour regions based on this NTRK quantity, and also a PT of electron and muon system. Non-prompt lepton background is estimated using contour region where 1 lepton fails lepton ID criteria. And the results, you can see, the measured cross-section is in agreement with prediction by Herrick 7. It is maybe a bit, the difference is a bit more than 1 sigma, but still the mu is equal to 1.33, and the significance, observed significance is 8.4 sigma. This result really may serve a very powerful part of input into the EFT combination and EFT interpretations. Okay, so I'm moving to my summary. The precision run-to analysis with really exciting results are coming out. Chosen recent results from TOP and Electroweak measurements were presented by me. Results are still in agreement with standard model, however, some tensions exist. Limits on anomalous coupling become important result from any Electroweak measurement and powerful tool to constrain the beyond standard model, beyond the models beyond standard model. And tests of standard model become more and more powerful, and it seems that the new physics science are really nearby. And I want to say that LHC round 3 is approaching, and we will have more data to find them. Okay, thank you.
Thank you, Professor Soldatov.
And greetings from Moscow.
No hands raised, no Q&A. I have a question, almost like curiosity. What is the status and futures perspective for, I know this wasn't featured in your talk, but for the W mass measurement?
Okay, it is, the work is ongoing, but maybe you know that the first measurement taken several years, actually. 4 years or something like this. So it is a very long work, really great work that was published by Atlas. But the work is ongoing, of course. Yeah.
Okay, thanks a lot. If no further questions, thanks again.
Thank you.
You can move to the next presentation, also from Atlas. It's from Chikuma Kato, which I believe is connected.
Oh, yes. Can you hear me?
Yes, I hear you very well. Tell Chikuma Kato obtained his PhD in 2018 from University of Tokyo, and during his PhD, he participated in many Atlas analyses, essentially contributed to the 2017 Higgs 2BB first 3 sigma evidence paper. Now he's a TDLE postdoctoral research fellow at TDLE Institute and responsible for muon condition data project of Atlas. Marcel?
Yes, let me share the slides. Okay, thank you very much for the introduction. Can you see my slides and can you still hear me?
Yes.
Okay, thank you very much. Greetings from Tokyo. Good afternoon, good evening, or maybe good morning. Today I will present the precision standard model Higgs measurements at us. This time I will highlight the who runs the Higgs measurement to test the standard model. We have basically total and fiducial, differential, and simplified template cross-section measurement to test the standard model. For example, we can constrain the coupling modifiers and the EFT coefficients and the other BSM tests. In this page, I have theoretical prediction plots. On the left side, the cross-section, and the right side, the branching ratio. Basically, we multiply these values and compare to the measurements. This is the reminder of the SDXS. Basically, the SDXS are the Higgs boson production cross-sections in the exclusive kinematic bins. Bins are split from main production cross-sections in this rapidity region, and bins are more split depending on stages, depending on analysis sensitivities, like stage 0, stage 1. Currently, the latest the binning is the so-called 1.2 binning. Basically, GGH high PT bins are important for the BSM. The low PT bins are also important for the couplings. And the VVF now uses the PTH instead of PTJ1. This is to harmonize with GGF, and MJJ bins are important for the BSM. And the VH high PT bins are again important for the BSM. And the NJET bin split are defined here, but in the current analysis, it's not yet split. And we also started to split the PTH in TTH. So let's check the results. Let's start from H1 gamma. This channel is great because it has sensitivity in all channels. And we use diphoton primary vertex using the tracking information and position observation in the neural network, achieving 76% efficiency for the GGH. Okay, now I can see my slides. And then after our selection for the rapidity H in less than 2.5 signals, we achieved about 39% efficiency. And the main backgrounds are the gamma gamma and gamma J and JJ. And the J is from the fake, and it goes to 30% level in the high mu. Left side are the plots comparing the different signal regions. In this plot, you can already start to compare the signal yields, which is very interesting. And in this round, we have the improvement in the categorization using BDT classes to separate the SDXS signals, and then the BDT categories to separate signals from continuum background in each class. This is the cross-section measurement. For the left side is the stage 0 main production cross-sections, and the right side is the reduced stage 1.2 binning SDXS. Inclusive cross-section times branch are reported like this. The VVF, WH, TTH plus TH significances are reported like this. And then in this measurement, what is important is the correlation between GGF and VVF, for example, and we report 40% correlation. This is compared to the previous round, this is achieving 30% improvement. So this is very nice and improving the precision of the measurement. Okay. Now let's also check the CP structure using the TTH gamma gamma channel. Basically describing the top Yukawa by like this. We can probe the CP structure of the top Yukawa. Left side is the just the inclusive signal regions, but there are 12 hadronic and 8 leptonic regions, and using the background rejection BDT and also CP separation BDTs. TTH now reports the 5.2 sigma in the observation, and TH is now limited to 12 times standard model. Now pure CP odd, basically the alpha 90 degree is now excluded at the 3.9 sigma. CP mixing angle greater than 43 degrees excluded as 95% confidence level. The standard model basically is here. The excluded pure CP odd is here. And then let's move to HCZ. This analysis selected Higgs boson candidates in the mass 4 lepton from 115 to 130, and also uses the sideband events to constrain the background. To improve the mass reconstruction, matrix element based pairing is used for the events with more than 4 leptons, and the FSR correction is also used. And then we categorize event and fit the neural network output for the separation and the measurement. Inclusive cross-section times branch are reported like this, showing quite good agreement compared to the expectation. These values. The dominant systematics are the lepton efficiency, luminosity, and pattern shower. So again, middle plot is the main production cross sections, and the right side is the SXS. And the SXS results are also used to constrain the EFT coefficients. Some plots are in the backup. I will mention it later. Then let me also highlight some of the total cross-section measurement and the differential cross-section measurements. This is combining H gamma gamma and HCZ results. The total cross-section and reported 55.4 picobar, and compared to the standard model, this is also showing quite good agreement. And we found H gamma gamma HCZ are compatible with each other, and the combination is also in good agreement with the standard model. And HWW to ENU MENU. This analysis targets the GGF and the BVF signals. And for GGF, we have 0, 1, 2 plus jet categories, and we use the MT for the final discriminant. And the BVF, we have 2 plus jet category, and we use the DNN output. The cross-section times branch are reported like this, and the right side is SXS. This WW providing sensitivity in the stat dominant high PT region, and also the VBF. So this is also very nice and interesting results. Then let's move to VHVB. Personally, I like this channel. There are 0 lepton, 1 lepton, 2 lepton channels from left side to the right side. And we use new signal region definition using the PTV versus the RVB, and the PTV split at 250 GB. This is to improve the correlation in the SXS signals. Then in this round, we have many improvements. For example, now 2 lepton kinematic fit using the soft track information, and a new VGT using new variables. yeah, basically using the soft track in the kinematic, we improved the mass resolution of the gluon ZH signal, and using new variables, for example, B tagging, soft track information again, and yes, 2-lepton polarization variable. We achieved a lot of improvement in BDT. We also optimize the BDT using current MC-stat and the new algorithm and so on. And then the W plus jet and p-pbar MC shape modeling are now updated to use the new method, so-called using the BDT. And we also use 2-lepton top EMU control vision to model the top background. Yes, this is the signal strength. Left side, the WHCA signal strength, and the right side, the 5POI STXS measurement. Basically, as usual, we maximize the likelihood to determine the parameter of interest. And now WH and the GA significances are 4.0 and 5.3. Reporting the strong evidence for WH and the observation of CH. Yes, now VH combined signal strength is measured with about 80% level precision in the Hryn'ova results, and the WHCH STXS are measured with 30 to 85% precision. And then let me also highlight the so-called EFT interpretations. Basically, we parameterize the cross-section times branch by using this SM-EFT approach, and the constraint so-called this C with some coefficients parameters. In the VHBB, this CHQ3 is the important one, which changes the cross-section of the QQVH high PT. We have good sensitivity there, so this parameterized constraint down to a few percent level. And the CDH changes the HBB decay, but the change is small, and the weaker constraint is reported. Yes, left side is the 1D parameter scan. And currently, we consider the dimension 6 operators, and including the quadratic terms. The change is reported like this green curve, and similar level is similar effect can be expected when we include the dimension 8 in terms. Currently, it is not included. The combination. Combining all the production modes and decay modes, we can achieve the best sensitivity, and these results are very interesting and important. So left side is all the production modes and the decay modes, and the right side is the STXS reduced to stage 1.2. Global mu is reported 1.06 plus minus 0.07. And the first observation of the WH is now reported, and the TH is now limited to less than 8.4 times standard model. Okay. And then let me also highlight some of the interpretation of the combined results. Left side is the generic parameterization, assuming no new particles in loops and decays. And the right side is the generic parameterization, including effective photonic gluon couplings with and without BSM contributions in decays. First from the left side, all coupling strength scale factors are compatible with the standard model. And the right side, now the invisible and the undetected branches are limited to less than 0.09 and 0.19. The results are also used to constrain the EFT coefficients and to the parameters in the 2 HDM models. Some plots are in the backup. Okay, in summary, I highlighted the Hryn'ova Higgs precision measurements. We measured the total fiducial, differential, or simplified temporal cross sections to test the coupling modifiers and the UFT coefficients and the BSM models. And the main production modes are now observed with greater than 5 sigma. The top and bottom UCAL couplings are also established in round 2. No significant deviation from the sun model so far. New results, more channels, and the combination and interpretation are actively developed. Thank you very much.
Thank you. Because unfortunately we have no time for further questions, but there is a question for you in the Q&A button, if you can kindly interact with the person asking. Would much appreciated. Once again, thanks a lot for a very nice presentation. Unfortunately, we have to move on to keep with the schedule.
Okay, thank you very much.
Thank you.
Oh, Mike.
Now we go to the last talk.
Thank you. Can you see my slides and hear me?
Sure.
Good. Okay.
Sure.
Go ahead.
All right. So I want to thank you very much for the opportunity to talk about this project, which is under development as a letter of intent to CMS for run 4, the high luminosity era, to search for new long-lived particles in the very forward direction. It's called FACET, which stands for Forward Aperture CMS Extension. So it's a new subsystem for CMS we propose. Formerly it was called the Forward Multiparticle Spectrometer. So I'll show you, this is a region between the superconducting dipole D1, which is at 80 meters downstream, and the TAX N, which is absorber in front of the superconducting dipoles, a machine at Z of 127. So there's 40 meters, basically a straight section with very little in there. What we want to, but it's a beam pipe that is nominally a radius of 12.5 centimeters, and we're proposing to increase it to 50 centimeters to have an 18 meters long vacuum tank, basically 18 meters long and 50 centimeters radius, to look for decays of particles that have come through the steel of the magnets. I'll show you more about that. So LHC quality vacuum, which means you have no background from interactions of particles in air or something like that, followed by CMS upgrade quality tracking, calorimetry, and muons. The main motivation is to search for these long-lived particles that penetrate 35 to 50 meters of steel and decay in this vacuum with masses up to about 25 GeV. Multiparticle decays, for example, c-c-bar or tau-tau and so on, would have very little background. We're aiming for essentially zero background in many of these channels, and lifetimes longer than you get in the central detectors, so c-tau up to 100 meters and so on, with full luminosity, 3 inverse attobarns. In addition, there's some physics of standard model physics that comes in parallel if you have low pileup runs or heavy ion runs, measuring forward charged particles that come through the D1 aperture, they get bent by the D1 and we can measure them, but we don't identify them as pi kp. That would need transition radiation detectors that are not really available, but we can do some studies of J-psi production and helium, anti-helium, and so on. So slide 2, just some general remarks about new beyond standard model particles. So these must exist if dark matter is particles. Do they interact with standard model particles other than gravity? Now, as you know, there are a lot of searches at the LHC in the high mass region. No discoveries yet, unfortunately, but that focuses maybe they're light actually, but with very small coupling to standard model particles, weak coupling or even not so weak coupling. And if they're light, they forward production is actually favored in many ways. So there are many theoretically motivated possibilities. You can have a vector which is spin 1, like a Z primed or dark photon that mixes with photons and would be produced in any process that produces photons. It can produce these dark photons if it's kinematically allowed. Then you can have spinners set 1/2 like a heavy neutral lepton, or scalars like a dark Higgs or dark pseudoscalars or axion-like particles. Now, our search is inclusive for anything that penetrates and decays. So any of these types of particle. Now, of course, if they decay, that's not dark matter, but we call them portals to the dark world if they couple to both standard model particles and dark matter particles. As I said, production, any source of photons like pi0 and eta decays, eta prime decays, if the mass of the dark photon is less than about a GeV. Now, for such light particles, fixed target experiments like at the SPS, like Na62, have higher luminosity because of the beam dump, so they have more sensitivity than we would. But for higher mass things above a GeV and so on, the LHC can be favorable. And you can get these dark photons coming from Bremsstrahlung, from quark Bremsstrahlung, or p-pbar annihilation, or quark gluon to quark gamma star, and so on. And then, of course, a dark Higgs could come from C and B decays if it's light enough. The bottom right plot shows calculations from Berlin and Felix Kling, showing the cross-section expected for dark photons for different processes. So above a GeV, you have sort of Bremsstrahlung and Verlian coming in, and so on and so forth. So now I'm talking about the real estate here. So the top picture shows on the left a little box showing the central CMS detector. And then you have a set of, going down the beam line, set of quadrupoles for focusing the beams, and then this D1 dipole at about 80 meters. And then there's nothing until you get to the tax N absorber at 127 meters. It's just a pipe there. I show a picture of this pipe as it was. We put in some forward shower counters down there for rapidity gap physics some time ago. So that is what we're proposing, to replace that pipe with one that is a diameter of a meter, radius of 50 centimeters, 80 meters long. This is the only change required to the LHC. Now, it's not unique in the sense Alice has got a similar big pipe, and the LHC have said provisionally this should be okay, but subject to a detailed study that they haven't done yet because CMS would have to ask them to do it. But we don't need any special running conditions. We want to run at high luminosity. And you see on the left a sketch of the dipole magnet, which is 35 Tesla meters. It's a very strong magnet, and that bends charged particles to the left and right out of the acceptance of our detector here. So the next slide shows a sketch of the proposed detector. The collision region is way off to the left, and then this shows the 18-meter long section of pipe as a decay volume. Neutral particles have come through not only the magnets, but additional shielding. And then there's a hodoscope in front of the pipe window that has to be very efficient because we want to detect basically every muon that comes through, or every charged particle that comes through, and tag them. And then at the back of this big pipe, we would have a very thin window, 0.5 millimeter beryllium, to minimize any scattering in there, followed by silicon tracking over 3 meters and timing, precision timing, and then the modules of the calorimeter, the HGCal type modules. We want to have only the same types of modules as the upgrade. More silicon tracking and a toroid at the back, which I sketch at the bottom left there. That toroid is to measure the momenta of muons that get through the HGCal so that we can actually get mu pair masses, because we don't have any magnetic field on the charge tracks in front of the tracking there. We just get the tracks very precisely, so we can get a vertex very precisely in the vacuum. And the next slide shows at the top a sketch of the pipe section. At the front, it's a conical increase for reasons of impedance matching, so that the machine doesn't see sharp edges. And at the back, we want a thin window, but we would put a conical wire grid in there so that the beam doesn't see a sharp edge there from impedance point of view. And then we're starting to do general simulations. You see at the bottom, the Turkish Istanbul group are doing this. They're part of this project. So then the next slide shows charged particles that go through the vacuum pipe and through the D1 aperture, which deflects them to the right and left. And they cover small areas. You see this on the left, you see positive particles to the right. That central hole is the pipe with a radius of 18 centimeters, and on the left. So all the regions that are not shaded in here, the clear region, only have particles coming through steel and no direct particles. Of course, you can have particles coming from interactions in the magnets and the beam pipe and so on that gives a background that we want to suppress. So these simulations done with DPM-Jet and Fluker. Now, we want to be inclusive and search for highly penetrating anything, decaying to all these different final states. Gamma is going to be tricky because you don't have such a precise vertexing, but you have some possibility there. But in charged particle pairs, E pairs, E mu, mu pairs, and so on, tau pairs, we get a vertex very precisely from the tracking, which has a resolution of about 30 microns per plane over 3 meters. And then again, if the mass of the particle is above 4 GeV, you kind of have CC bar decays or a quark pair decays. And that's like a charm factor in E plus E minus, those events just boosted to TeV. So now we have neutron and K long background, but we are having ways of minimizing that and hopefully reducing that to manageable levels. So one more slide on distinct classes of long-lived particles. So I would say class A is involving massive states like the standard model Higgs or heavier Z primes and so on. And here, the large central detector solid angles are favoring these states at high PT. But class B, I say, is only light states, like less than about 10 GeV, and their low PT and forward production is favored. And the right parameters is delta Y, delta phi, rather than delta omega, and so on. So one class is calculated by Du and Liu and Van Tran here, which is calculating actually from a Z prime decay with some particular parameters, how many events we would get. This is into mu pairs actually in 3 inverse Aldebarans. Now 5 and 15 events is not super large number, but if you have 0 background, that is discovery level. And we have 0 background in these channels. On the right, you see calculations of the decay of a dark photon, minimal dark photon, if you like, to different channels. And you see by the time you get to 10 GeV on the right-hand side of that plot, you have equal numbers of E pairs, nu pairs, and tau pairs, and then which total about 45%, and then multihadrons is 55%. So obviously something decaying to multihadrons in this vacuum is going to have very little background. I mentioned before that for light particles less than a GeV, beam dump experiments have higher fluxes. The plot on the right shows in the PT Feynman X plane the density of pions expected from that. There's quite a bit of uncertainties in this because there are no basic measurements about that. But on the bottom right, you see various classes of dark photon production from Bremsstrahlung, QQ-bar annihilation, meson decays, and Drolian, and so on. So there's references there. There's a lot of papers about this. Bora in Istanbul has done some calculations of the reach using EPOS in the mass coupling plane for FACET. And you see in the pale green there that these dark photons at GeV and above come largely from Bremsstrahlung, and this is preliminary calculation. And now about heavy neutral leptons, which of course another thing we'd be sensitive to. They can come from a Z prime going to heavy neutral leptons. There's papers there, and Sushita Kulkarni has done a study for our geometry, and you see on the bottom right plot as a function of the mass of the heavy neutral lepton, 5 to 30 GeV, and the coupling V mu n. You see the reach in FACET calculated in the pink thing. The other lines are phasor 2, the phasor upgrade in green, and the Codex B and MAP. These are not approved experiments, of course, neither are we, and Methuselah, which is also not approved. The only one of these that's approved is LHCb, and this is assuming they should have quite a bit of background, so it's assuming a sort of pessimistic background there. But you see that the FACET reach up to above 20 GeV with in these couplings for heavy neutral leptons, which could decay then. I mean, there can be, of course, muonic, tauonic, and electronic heavy neutral leptons decaying in different ways. And a typical decay for the muonic one could be to a muon and then a QQ bar from the W star that is decayed. So you have events like that, where you have 5 many charged tracks there from a vertex. So that the thing is that we have a large decay volume compared with phaser, for example, and we're 4 times closer in, bigger solid angle and so on. And a few slides about what other things we might be able to see, like tau tau. Of course, you know, the taus decay with neutrinos missing, but there are decay like E. What the 2 taus one can decay to an electron, the other to a muon. So you have an E mu. They wouldn't come from exactly the same point, but fairly close, because the taus, even though they're boosted, have a short lifetime. Or you can have 1 tau decaying to 3 pions and the other tau decaying to a lepton or neutrinos. So you have those signatures. Now, of course, the missing neutrinos smear the direction of the primary a little bit, but still, those would be spectacular events. Also, CC bar and BB bar events. Now, we're simulating these in more detail, but the simulations are still in progress. But the background should be very small for these. Even for dijet, if you have an X with a mass of 10, 20 GeV decays to dijets, then you'll see displaced dijets. And of course, in the central detectors, we look for those, but here we can look for them with the parent traveling, 100 meters and then decaying over this 18-meter volume. Gamma gamma, like axion-like particles, the critical issue here is pointing with the showers and showing that the vertex came from within the vacuum pipe. This is, of course, not so good as with tracks, but the right plot shows a simulation of the CMS of two photon showers in the upgrade calorimeter, the electromagnetic part of it. There's a 280 GeV shower separated by only 3 centimeters, and you can reconstruct the directions quite well. Of course, the background from this can come from pairs of pi zeros. Of course, they decay very promptly, so the gammas from those would come from right at the very front of the pipe. But you can have pile up sort of background here that needs to be studied. But the photon energy resolution should be very good. Now, here's one comparison, because phaser is approved for the next run, and they're proposing phaser 2, which is longer detector, 480 meters to 485, so that's 5 meters long. So 480, and then FACET, which is 18 meters long and 101 to 119 meters. And this is just as a function of the boosted lifetime of a particle, so a gamma c tau, what the probability of decay within the volume is. So it's not talking about production cross sections. Phasers at 0 degrees, around 0 degrees, and we're at 1 to 4 milliradians, so slightly higher angle, but the solid angle factor is 4. Anyway, so because phaser got this area started, so that's very, very good, and they've been helpful in helping us. So then we want to have precision timing as well on the tracks, like 30 picoseconds or better. So we plan a timing layer, probably based on LGADs. And there are 2 different reasons for this. One is that when you have 2 tracks, you want to check that they're in time as well as in space, so 4-dimensional vertexing. And because 30 picoseconds is like a centimeter there. And unfortunately, well, the time of flight on a neutral particle would be valuable if if you have, of course, the collision time spread is about 200 picoseconds in one interaction. We have 150 or so interactions per bunch crossing, so we don't know what the time origin was. But the bottom plot shows the time difference between a particle with different momenta, different masses. So look at the top orange plot, for example, which is for a 10 GeV mass particle, and at 500 GeV momentum, it's 100 picoseconds later than a neutron would be. But if its momentum is down at 100 GeV, then you're starting to get quite a useful time of flight measurement, which gives you some extra constraint on the mass of the particle. So that's 2 reasons for wanting good timing. So integration with CMS. So as we're proposing it to be a new subsystem that's fully integrated into CMS, even though most of the high luminosity events we couldn't correlate with the central detector events, but all the detectors would be identical to the planned CMS upgrade detectors. And the area we want to cover is about 6% of the area of the upgrade detectors. So It's sort of almost at the level of the spares that's being produced. But so we don't need any separate R&D. DAQ would be the same. And we'd read out these detectors with all CMS events, but we'd have a separate level 1 trigger. We want to be sensitive to every bunch crossing, of course. And so we can make a local trigger requiring at least 2 tracks from a vertex in the vacuum without incoming charged particles in line, and so on and so forth. And then that rate should be acceptable, but if it's not, then if it's too high even, then we can send FACET-only data to a separate stream. The events will be very small. And then if we have low pileup data running for PP or proton-oxygen, oxygen-oxygen, if they happen, then correlations become very important because we can study forward charge particles in the spectrometer correlated with central detector. The next slide just shows a list of some links. We had 2 dedicated workshops last year, and some various talks are given there. And we have bi-weekly meetings developing this letter of intent on simulations and so on. And as a contact, Denny Sersi there, who's organizing those meetings. She's with Adıyaman University in Istanbul. And Greg Landsberg gave a presentation to CMS plenary. But we're hoping that the CMS management will interact more with the LHC to check that the beam pipe and so on, how much it would cost, and et cetera, et cetera. So I'm nearly finished, but the strengths of the long-lived particle search, we have this large volume of vacuum for decays, a meter diameter, 80 meters long, and it's LHC quality vacuum. So we don't have to worry about interactions of particles like neutrons, and there are plenty of those in the gas. High precision imaging calorimetry, all that shielding in the direct path. So no direct charge particles over nearly all the area. They're swept aside by these magnets. And then boosted lifetimes up to kilometers. Unboosted would be 1 meter to 100 meters and so on, depending on the momentum spectrum. And basically masses of a GeV to 20 GeV or a bit more, especially above the region of the fixed target experiments, ability to reconstruct multi-particle decays. And in certain channels, we expect to have essentially no background. So even half a dozen events, or it could be a discovery here. So it's complementary to all the LHC's central detector searches and other search experiments like fixed target and LHC ones that are proposed. So my last slide is a summary. Forward multipath spectrometer under development, unique potential in 3 inverse autobahns. I've said these things, so it's basically clones of the proposed detectors. There's many opportunities to participate, and if you're in CMS, you may want to join us on that. And thanks to some colleagues at the LHC who've been calculating things for us with Luca. Thank you. Questions? Alberto, I see your hand raised.
Yes. Michael, please, could you send to me some documentation about the facets?
Yeah, absolutely.
And who is the collaboration?
So, well, we have about 20 people who are active and meeting every couple of weeks. So Bora Izildak from Istanbul, sorry, Suat Oskuruklu from Istanbul, professor there. Greg Landsberg at Brown University. Andres Skuja at MIT, right? And well, Dan Green and myself from Fermilab, we're both emeritus, so we almost don't count. But these sort of people, I can send you a draft of the developing document, Alberto, and it'd be very.
Yes, I would like to thank you because I would like to read carefully and see what you can do also.
Yes, I mean that'd be great to. So we can have a discussion as well. But I'll send you after this LISHEP meeting next week or so. But I'll send you some documentation about it. Okay.
Okay. Thank you. And thank you also, Philippe.
Hello. There's no further questions, so I guess I give back the word to you, Santoro, so you can close this section. Thanks a lot.
Okay. Thank you very much for all speakers of this afternoon. We can profit of the talks that was very, very good. And we hope that you will have courage for tomorrow, attend also LISHEP. And one thing that I would like to call attention to everybody is, please maintain your time, because if not, each day we will go, because if one gets some delay, is a cascade. After comes one after other, and so it's additional. But it's okay. And thank you very much. Javi, you want to see a word for today? Something?
Yes, I'd like to thank everybody. I think these were a wonderful range of talks, and some speakers went into a lot of depth, including based on their own experience, which I found very valuable. And I also wanted to especially thank the speakers this morning for the introduction from multiple perspectives to so-called AI and machine learning, which will have increasing impact on our field and on many of the searches and measurements that we saw. Thank you.
Okay, then today's close session C of LISHEP 2021. Thank you very much.
Thank you, Alberto.
Ciao, Alberto.
Thank you. Bye-bye.
Thank you. Bye.
Eduardo, you stay? Because we would like to talk.
Yes, I'm here. You can go to another room? No.
You can stop